Picture a floor of black mud 360 million years down, where no light has ever fully reached. The water above it is warm, warmer than any sea you have swum in, somewhere in the high 70s to low 80s Fahrenheit. Out of the murk, without sound, a wall of bone slides into view. It is the front of an animal, a head cased entirely in armoured plate, blunt and broad as a doorway. There are no lips on it, no soft face, no teeth in the way you think of teeth. Instead, there are two long blades of bone, self-edged, that can swing open and snap shut in about 20 milliseconds. That is faster than you can blink. This is Dunkleosteus terrelli, and it is swimming these tropical shallows roughly 130 million years before the first Tyrannosaurus rex will ever draw breath. Let that distance settle for a moment before we go on. You are not looking at a dinosaur. You are looking at something far older, a ruler of the sea from an age when nothing at all walked the land in any real sense. If dinosaurs feel ancient to you, and they should, then hold this thought gently as you rest tonight. The gap between you and a T-Rex is smaller than the gap between a T-Rex and this armoured fish. We are peering back past the dinosaurs, past their ancestors, into a world of water and silence that has almost no landmarks you would recognise. Stay with me here at the beginning, because this is a slow walk and there is no hurry in it. You do not need to remember anything. You do not need to follow a thread or hold a fact. Let the numbers and the names drift over you like current over stone. If you find this quiet company useful, the kind you can fall asleep inside, that is the whole point of the hours ahead. We are going to move through deep time at the pace of breathing, and the armoured fish will still be here when you wake, so let us set the clock properly. Dunkleosteus terrelli lived in the Late Devonian, a stretch of Earth history that ran roughly from 382 million to 358 million years ago. Say those figures slowly. 382 million years. The number is so large it stops meaning anything, and that is fine. What matters is the shape of it. The dinosaurs, the ones you know from every museum hall, would not appear for well over 100 million years after this fish was already old news. The first of them would rise around 230 million years ago. Dunkleosteus was ancient before the dinosaurs were even a possibility. The Devonian has a nickname, earned honestly, and paleontologists still use it. They call it the Age of Fishes. For tens of millions of years, the great evolutionary experiment on this planet was happening underwater, in the bodies of fish. Jaws were still a relatively new invention. Backbones were being refined. Fins were finding their shapes. Whole lineages of swimming animals bloomed and spread across the world's oceans and lakes, and some researchers describe this surge with a phrase of its own, the Devonian nekton revolution. Nekton simply means the animals that swim freely through open water, the ones that move under their own power rather than drifting. During the Devonian, that open water filled with life as never before, and near the top of it all sat the placoderms, the armoured fish, with Dunkleosteus among the largest and most fearsome of them. Now let us build the world around this animal, so you can stand inside it. The first thing to understand is that the map is wrong. If you imagine Ohio, you probably picture cornfields, grey winters, a landlocked stretch of the American Midwest. Forget all of it. In the Late Devonian, the land that would one day become Ohio was not in the north at all. It lay south of the equator, drowned beneath a warm, shallow tropical sea. The continents were arranged in patterns you would never guess, drifting slowly across the face of the globe, and this particular patch of crust was basking in equatorial warmth, submerged under gentle salt water that never froze. There were no polar ice caps for most of the Devonian. Think about what that means for a planet. No white crowns at the top and bottom of the world, no great sheets of ice locking away the seas. The ocean stood higher, spreading in warm, shallow shelves across low continents, and the global thermostat sat turned up, mild and even from pole to pole. The sea over ancient Ohio would have felt to you like bath water, left a little too long, warm on the skin, heavy and still. You could have floated in it for hours without a chill. At the surface, sunlight came down clear and slanting, cutting through the upper water in long, soft columns. Near the top, life was everywhere and the light was generous. But follow that light downward and watch it weaken. Below a certain depth, the water grew still and dark and the oxygen thinned toward nothing. Down there, on the very bottom, lay a floor of fine black mud, cold and lifeless in its chemistry, so starved of oxygen that almost nothing could live in it. This is important, and we will return to it many times because that black anoxic floor is the reason we know this fish at all. Its fine sediment would harden over unimaginable spans into a rock called the Cleveland Shale. The best Dunkleosteus fossils on Earth come out of that shale, from northern Ohio, from layers dated to around 362 to 361 million years old. Hold the two halves of this sea together in your mind. A bright, busy, sunlit ceiling of warm water, teeming with swimming life, and beneath it, a silent black basement, where oxygen ran out and stillness ruled. Between those two worlds moved the armoured fish, and in that dark basement one day, its body would come to rest and be kept. Listen to the world for a moment, because the silence of it is unlike anything you have ever heard. There is no birdsong here. There cannot be, because there are no birds and there will be none for hundreds of millions of years. There is no hum of insects carried out over the water from the shore. There is no voice of any kind that you would recognize as a voice. The land itself has almost nothing on it that could make a sound. So the soundscape of this sea is purely physical. The slow push of current, the soft collapse of water against water, the muffled percussion, deep and low, when something large closes its jaws on something else. That is all. A world of true quiet, broken only by movement, because none of the noise-making creatures of later ages have been born yet. If you turn toward the distant shore, you would see a coastline that is green but strange. The Late Devonian was the age when the first true forests were rising, and they were dominated by a tree called Archaeopteris. It grew tall for its time, with a woody trunk that could measure more than a yard across. Real timber, real bark, spreading fronds that cast the first deep forest shade the planet had ever known. Around it grew lycophytes, giant relatives of the club mosses, and towering horsetails and ferns, all crowded along the wet margins of the land. But it was a low skyline, primitive and simple compared to any forest you have walked through, without a single flower in it, no blossoms, no fruit, no grass underfoot, because grass would not exist for a couple of 100 million more years. And past the plant line, the land went barren, stony, bare, quiet. Nothing walked there in any meaningful way. No reptiles, no mammals, no amphibians as you would know them. Only at the very end of this long period would a few pioneering creatures, the ancestors of all land vertebrates, begin to test the shallows and the mudflats, hauling themselves half out of the water on stubby limbs. In the world of Dunkleosteus, the shore was mostly empty and silent, a green fringe backed by bare rock, and everything that mattered was happening in the sea. So return to the water and let us fill it with life, because it was crowded. The Devonian Ocean was not empty around its armoured king. It swarmed. Through the sunlit upper layers moved great numbers of jawless fish, ancient lineages that fed without ever biting, sucking and filtering along the bottom or through the water. Among them swam the newer jawed fish, the innovation of the age, mouths that could open and close and seize. Their diversity was exploding, filling niche after niche, and the sea rippled with their movement. Drifting and jetting through this same water were the ammonoids, coiled cephalopods sealed inside spiral shells, distant relatives of the living nautilus and of the octopus and squid. Some hung nearly motionless, adjusting their buoyancy with gas inside their chambered shells. Others pulsed backward in short jerks, squeezing water through a fleshy funnel, their coiled forms turning slowly in the current. They came in a great range of sizes and their shells, thick and ribbed and armoured in their own way, made them a challenge to eat. For most predators, that shell was a locked door. Remember that, because for the armoured fish it would not be a door at all. And then there were the shapes that made the smaller fish scatter, the arthrodires. This was the group of armoured, jawed placoderms to which Dunkleosteus belonged, and their silhouettes were unmistakable. Where a shark tapered and flexed, an arthrodire led with a box, a head sheathed in interlocking bone, heavy and blunt at the front. You could tell them at a glance, even in murky water. Among them cruised a sleeker neighbour, Cladoselache, one of the earliest sharks, a streamlined swimmer around 6 feet long. It hunted small fish and cephalopods and shrimp-like creatures, and its body was built for speed and grace in a way the tank-headed placoderms were not. 2 different designs for the same warm sea, one slender and quick, one armoured and slow and terrible. There was also, moving through these waters, a giant that rivaled Dunkleosteus in size but not in menace. Its name was Titanichthys, another huge arthrodire placoderm, and in older reconstructions it was thought to match or even exceed Dunkleosteus in length. But its lower jaw was narrow and toothless, without any cutting edge at all. In 2020, a team of researchers proposed that Titanichthys was not a hunter of large prey but a filter feeder, cruising open water with its mouth agape, straining out swarms of tiny fish or clouds of drifting plankton. If they are right, it was among the earliest large filter-feeding vertebrates known, a gentle giant sharing the sea with a violent one, the way whale sharks share today's oceans with far smaller and far fiercer things. Into this crowded, warm, silent sea placed Dunkleosteus as the shape the others feared. We will not open up its anatomy tonight, not the details of the plates or the blades or the strange half-cartilage skeleton hidden inside the armour. That is a country we will travel through slowly, later. For now, simply hold the impression of it. The apex placoderm, the animal at the top, a head like a battering ram of bone, a mouth that worked without teeth, moving through the water with the unhurried confidence of a creature that nothing else could threaten. When that armoured silhouette resolved out of the gloom, the smaller fish had one instinct, and it was to be elsewhere. How big was it, this ruler of the Devonian shallows? Here you must be careful with me, and this is where the honesty of the science matters, because the honest answer has changed in recent years. For a very long time, the popular picture of Dunkleosteus was of a monster 20 to 33 feet long, weighing well over a ton, a fish the length of a school bus. Those figures came from taking the one part we actually find, the armoured head and thorax shield, which runs a bit over 2 feet in length, and scaling up the rest of the body as if it were built like a shark, long and tapering behind the head. But here is the quiet problem that sat under those old numbers for decades. No one has ever found the back half of a Dunkleosteus, not once. The armoured head and shoulder region fossilise beautifully because they are made of thick bone. The rest of the body, softer and largely built of cartilage, almost never survives. So every long, shark-like reconstruction of this animal was in truth a careful guess, an educated extension of a head into a body no one had ever actually seen. In 2023, a researcher named Russell Engelman, working at Case Western Reserve University in Ohio, took that guess apart. He measured the proportions of smaller related arthrodires whose complete bodies we do have, animals preserved from nose to tail. Then he applied those proportions to Dunkleosteus. His conclusion was startling. Instead of a long sea serpent of a fish, he argued for a much shorter, stouter, chunkier animal, something on the order of 11 to 13 feet long for a typical adult, with even the largest known individual reaching perhaps just under 29 feet as an extreme outlier. A tank, in other words, rather than a torpedo. Broad and powerful and compact, its enormous armoured head a larger fraction of a shorter body. I want to be plain with you, because plainness is a kindness at this hour. This revision is not settled. It is a live scientific debate, still being argued in journals and at conferences. Some researchers find the new, smaller Dunkleosteus persuasive. Others hold to versions of the older, larger estimates, or land somewhere in between. When you hear this creature called 30 feet long, and when you hear it called 13 feet long, both figures are honest attempts by careful people working from incomplete bones. The truth is that we do not yet know the exact size and shape of the most famous armoured fish that ever lived, and the not knowing is itself part of what makes it worth sitting with. Nature keeps some of its answers folded up inside stone and gives them back only slowly. Whatever its precise length, this was a heavily built predator with a bite that has become legendary, and rightly so. We will spend real time on that bite later, on the strange four-bar mechanism of its skull, and the speed of its jaws, and the crushing force at its blade edges, forces that biomechanical models place among the strongest measured for any fish, comparable to those of a large crocodile. For now, simply know that the armoured silhouette in the murk was not just large, it was fast where it counted at the mouth, and it was strong enough to shear through the shell of an ammonoid, or the armour of another placoderm as though cracking a nut. The soft-bodied things of the Devonian sea, and even some of the hard-bodied ones, lived their lives inside the range of that mouth. There is a rhythm to how such an animal would move through its days, and you can feel it if you slow down into the water with it. In the warm upper layers, hunting, turning that broad head toward movement. The unhurried cruise, the sudden convergence, the low muffled shock of the jaws closing, and then quiet again, the particles settling, the current resuming its slow work. Around it the ammonoids drifted on, and the jawless fish flickered in their schools, and the light came down in its soft slanting columns from a surface warmed by a sun that has not changed nearly as much as the world beneath it. This was the daily life of the ruler of a sea that no human eye would witness for hundreds of millions of years. And that brings us to the strangest and quietest part of the whole tale, the part that turns a fish into a story of survival across deep time. When a Dunkleosteus died, whether from age, from injury, from the violence of its own kind, its heavy armoured head would begin to sink. Down it went, out of the warm, bright ceiling of the sea, down through the fading light, down toward that black anoxic floor we spoke of. And on most of the seafloors of the world a dead animal is quickly undone. Scavengers arrive, currents scatter the bones, oxygen and bacteria break the body down until nothing coherent remains. Not here, not on the floor of the Cleveland Shale Sea. That black mud was so starved of oxygen that it could not support the scavengers and the busy decay of ordinary seafloors. The chemistry that made it lifeless also made it a keeper of the dead. A carcass settling into that fine cold sediment might lie almost undisturbed, its armour intact, its shape held, sometimes even faint impressions of softer tissues preserved against the odds. Layer upon layer of black mud drifted down over the centuries, sealing the body deeper, pressing it flat, beginning the slow chemistry that turned sediment to stone. What was a swimming animal became a shape locked in rock, waiting in the dark. This is why so much of what we understand about Dunkleosteus comes from a single formation in a single region, from those black shales of northern Ohio. The very conditions that would have been deadly to the living, the oxygen-poor depths, became the archive that kept the dead. Every plate of armour a museum holds, every reconstruction argued over in a journal, traces back to that patient black floor and its refusal to let the bodies rot. The sea preserved its king, without knowing it, without meaning to, in the one place on the bottom where nothing else could live. So let the scene close for tonight the way the water itself would close over that sinking body. The warm tropical shallows above, bright and crowded, the ammonoids turning, the early sharks slipping through the light, the armoured silhouette moving in its slow circuit near the top of everything alive. And below it all, the dark, still floor, gathering its sediment grain by grain, keeping its slow appointment with the future. The age of fishes rolled on above, tens of millions of years of warm seas and rising forests, and the long green fringe of the first woodlands. The armoured fish did not fade away into nothing when it died. It went down, and it was held, and it waited. Think of how long that waiting was, in a world that would keep changing overhead. The forest would spread and thicken, and then be devastated in the pulses of extinction still to come. The seas would rise and drain. The continents would grind northward, carrying this drowned patch of tropical seabed thousands of miles across the globe until it surfaced in time as dry Midwestern land under a colder sky. Whole kingdoms of life would appear and vanish above the buried armour. The dinosaurs would come and rule and be swept away in their own catastrophe, and none of it would disturb the fish sealed in its shale. In the long ledger of the planet, the rise and fall of the dinosaurs would pass over that black rock like a single turning of the light, a geological instant against the deeper span of the stone. Rest here a while, in the warm dark water, and let the count of years grow soft and meaningless. There is comfort in a number too large to hold. Nothing in your day, nothing waiting for you tomorrow, weighs anything at all against 360 million years of patient rock. The armoured fish is down there still, in a sense, in every fragment we have pulled from the shale, its blunt bony face pressed into the record of a warm sea that no longer exists. Pull back now from the animal itself, and let the whole sea open out around it. The water here is warm, warmer than almost any coast you have waded into. Across these shallow tropical shelves the sea sits somewhere in the 70s and 80s Fahrenheit, top to bottom near the surface, with no polar ice anywhere on the planet to chill the deep currents. For most of the Devonian, the Earth carries no permanent ice caps at either pole. The land that will one day be called Ohio does not lie in the north at all. It rests south of the equator, low and drowned beneath a broad, shallow tropical sea, and the sun that reaches it comes from a sky you would not recognize. Look up through that water and watch the light. Near the surface it is clear and bright, and the sunlight slants down in long moving columns, bending as the swell passes overhead. In the upper few fathoms you can see for a good distance, the way you can in warm, clear shallows today. The light is not white so much as a soft green gold, filtered and scattered by the living water. Small bodies flicker through those beams and vanish. The warmth soaks down only so far before it begins to thin, and the brightness with it. Listen and understand what is missing. There is no birdsong here because there are no birds, and will be none for hundreds of millions of years. There is no hum of insects carried out from the shore on a warm wind, because the great choruses of insect sound have not yet begun. No frog, no gull, no bark or call of any land animal reaches this water, because almost nothing yet lives on the land that can make such a sound. The whole vast category of noise you fall asleep to, the layered voices of a living countryside, simply does not exist. What remains is water, the slow wash of current over the bottom, the hiss and slide of the swell, and every so often, muffled and low, the percussion of something large closing its jaws on something else, a dull heavy thud that travels through the water and fades. That is the entire soundscape of the world, movement and the sea, and now and then the blunt music of a large animal feeding. Turn toward the shore, and the strangeness deepens. The coastline is fringed in places by the first true forests the earth has ever grown. These are stands of Archaeopteris, an early tree with a proper woody trunk, some of them more than a yard thick through the base, wider than the reach of your 2 arms around them. Around and beneath them grow lycophytes, tall club mosses, and giant horsetails ribbed like green columns, and low spreading ferns filling the shade between. It is a green skyline, but a low and primitive one, nothing like the towering canopies that will come in later ages. There are no flowers anywhere in it, no grass softens the ground, no fruit hangs from any branch. The forest is all stem and frond and spore, a quiet green built entirely without a single blossom. and these forests are doing something to the whole planet slowly, while the sea below goes about its business. Spread across roughly 50 million years, the rise of Archaeopteryx and its kin is drawing carbon dioxide down out of the air and lifting the level of oxygen, reshaping the climate of the entire world even as the great fish thrive offshore, unaware. The trees are quietly rewriting the sky. The sea does not notice. Walk your eye past the last of the plants and the land turns barren. Beyond the reach of the forests, the ground is stony and bare, swept by wind and rain with nothing to hold it. No animal of any size moves across it. The land vertebrates have not arrived. Only at the very end of this long period will the earliest ancestors of the four-legged animals begin to test the edges of the shallows, hauling themselves through weed and mud at the margin between water and air. For now, the shore is a threshold almost no creature has crossed. The great drama is still entirely underwater, and the underwater world is crowded. Sink back down into it. The upper water column is alive with fish, more kinds of fish than the earth has ever held before. This is the reason the whole period earns its old nickname, the Age of Fishes, for the sudden flowering of jawed vertebrates that fills these seas. Around you drift the jawless fishes, ancient forms that feed without ever closing a true bite, and among them move the early jawed kinds, testing a new and powerful invention on the world. Schools of small silver bodies bend and turn together, catching the slanted light in flashes. Through them drift the ammonoids, coiled shellfish riding inside chambered spirals, some hanging almost motionless in the current, others jetting backward in short darting bursts when something alarms them. Their shells are the crushable armour of this sea, thick and ridged, and later in life the great armoured predators will learn to break them open. For now they simply drift, tentacles trailing, tasting the water. They are among the most common things you would see if you hung here in the blue and watched. And then the silhouettes. Out of the brighter water larger shapes glide, and among them are the arthrodires, the armoured-jawed fishes of this age, with their heads and shoulders sheathed in interlocking bony plate. Dunkleosteus is the great one, its tank-like head shield unmistakable, blunt and heavy and broad. But it's not alone in its kind. Titanichthys shares these waters, another giant among the armoured fishes, and yet it lives an utterly different life. Its lower jaw is narrow and toothless, without any cutting edge at all, and many researchers now think it strained its food from the open water, sieving out clouds of small fish or drifting animals, one of the earliest large filter feeders any backboned animal is known to have become. Two giants side by side, one built to shear and one built to strain. Among these armoured shapes move the early sharks, and they are built to a different plan entirely. Cladoselache is one of them, a streamlined shark roughly 6 feet long, slim and quick, where the placoderms are broad and plated. Its fossils are so beautifully kept in this very seabed that the impressions of its muscle and skin survive, and the last meals still sit in its preserved stomach, small fish and soft cephalopods and shrimp-like animals swallowed headfirst for speed. Watching it cut past the armoured giants, you would see the deep old contrast of this sea laid out plainly. Heavy bone against smooth muscle, the old design against the shape of things to come. This is a good place to pause before we follow the great fish down into the rock and the long silence that waits there. If this slow walk through a vanished ocean is carrying you towards sleep, you can keep these episodes close by choosing to follow or subscribe wherever you're listening, on Spotify, on YouTube, or in your podcast app of choice. Then let the sea take you back down, because now you must go deeper, below the warmth and the light, to the floor of it all. As you sink past the bright upper water, the green gold fades, and the blue thickens and darkens. The warmth thins away, the movement slows, and down on the bottom, in the deepest and stillest reach of this basin, the water is not merely dark, it is dead. The mud there is black, fine-grained and starved of oxygen, an airless ooze where almost nothing can live. This is an anoxic deep, a still and lightless floor where the ordinary machinery of decay grinds nearly to a halt. That poisoned stillness is a strange kind of mercy, though nothing down there feels it. In a normal sea, when a great animal dies, the scavengers come, and the currents scatter the bones, and within days little is left but fragments. Here, on this black bottom, the scavengers cannot survive to do their work. The low oxygen kills the crawling cleaners that would tear a carcass apart. So when a body drifts down into that mud, hunter or hunted, giant or minnow, it settles into the ooze almost undisturbed. The soft outlines hold, the plates keep their arrangement. Even muscle and skin can leave their ghost behind, as they did for the little shark with its last meal intact. Layer by layer over uncounted years, that black mud thickens and compresses and hardens, and the fine dark sediment becomes the stone that geologists will one day call the Cleveland Shale. It is a marine shale, laid down in these northern Ohio waters somewhere around 362 to 361 million years ago, and it is black precisely because it formed in that oxygen-poor deep. Almost everything the world will ever learn about the great armoured fish comes out of this single dark formation, because this one still suffocating basin kept its dead so well. So hold the whole scene together for a moment before it closes. The warm bright shallows overhead, the sun slanting through in slow columns, the silent air above, empty of every voice you know, the low green forests fringing a barren shore, the crowded blue water column, its schools and spirals and armoured silhouettes, and beneath all of it, the black and airless floor, patient, still, receiving whatever falls. Into that quiet dark, one day, the greatest predator of this sea will also sink and settle and be kept. Yet for all its scale, this armoured ruler would wait in the dark rock for more than 360 million years, until a curious man walking a quiet lakeshore finally pulled its blunt face back into the light. Yet for all its scale, this armoured ruler would wait in the dark rock for more than 360 million years, until a curious man walking a quiet lakeshore finally pulled its blunt face back into the light. Yet for all its scale, this armoured ruler would wait in the dark rock for more than 360 million years, until a curious man walking a quiet lakeshore finally pulled its blunt face back into the light. His name was Jay Terrell. He was not a scientist. He kept a hotel and collected fossils the way other men collect coins, patiently, for the pleasure of the finding. In 1867 he was walking the southern shore of Lake Erie, near the small Ohio community of Sheffield Lake, with his son beside him. Picture that shoreline for a moment, because it is calmer than the sea that made it. The water laps low against a wall of dark shale. The cliffs are not tall. They rise only a little above the beach, layered and flaking, the colour of wet slate and old ash. Wind moves off the lake, cool and steady, and in that soft grey light, Terrell sees something that does not belong to any living animal he knows. Bone. Plates of it, weathering out of the black rock. Not small chips or slivers, but broad curved plates the size of dinner platters, thick and heavy, edged with a strange blunt architecture. He would have knelt in the shale to look closer. He would have run a thumb along a ridge of fossil bone that had not felt open air since the Devonian, and he had no name for the creature that wore it. So he gave it one of his own. He called it the terrible fish. It is a plain nickname, almost affectionate, the kind of name a man gives to something he cannot yet explain. But it was accurate. The plates in his hands had belonged to a predator, and the more of them he and later collectors pulled from those cliffs, the clearer that became. This was a head built like a shield, a mouth built like a pair of shears. Before we go further with Terrell, settle in and get comfortable. Loosen your shoulders. Let the pillow take the weight of your head. There is no hurry in any of this. The rock waited 360 million years to be read, and it will keep for the length of one quiet night. Let the names and the numbers wash over you slowly, the way that lake washed over that shale. Now, That black rock has a name of its own, and it is worth knowing, because almost everything you will ever learn about this animal comes out of it. Geologists call it the Cleveland Shale. It is a marine shale, a stone made from mud that settled on an ancient seafloor, and it is dated to roughly 362.5 to 361 million years ago. That is a thin band of time, barely 1.5 million years of settling mud pressed now into stone. The shale is black for a reason, and the reason matters. That mud gathered in still, deep, oxygen-poor water. On a normal seafloor, scavengers and burrowing worms churn through a carcass within days, scattering the bones, erasing the body. But this seafloor was nearly lifeless at the bottom. Too little oxygen for the cleanup crews to survive. So a dead animal that sank into that black mud was not torn apart. It was buried whole, sealed in fine sediment, held in place while the slow chemistry of fossilization did its patient work. That is why the Cleveland Shale is so precious. It is a formation that killed the things that would have destroyed its fossils. It preserved not only the heavy armour but faint impressions of softer tissue, cartilage and muscle that almost never survive. When you hold a specimen from that shale, you are holding the gift of a still, black, suffocating deep. The best examples of this armoured giant on Earth come from that single, dark band of Ohio rock, concentrated in what are now Cuyahoga and Lorain counties. Think of the geography of it. The cliffs Terrell walked were the exposed edge of that formation, sliced open by the lake and by the slow grind of Ohio weather. Freeze and thaw, rain and wind. Each winter pried the shale apart a little more, and each spring offered up another sheet of ancient seafloor to anyone patient enough to look. Terrell was patient enough. He kept collecting, and his plates made their way toward the people who could study them properly. But here is a curious thing about the pace of science. Terrell found those first plates in 1867, and the animal did not receive its full formal scientific name until 1956. Nearly 90 years passed between the finding and the naming, nearly a century in which these bones were studied, argued over, shuffled between other names and other groupings, before they finally settled into the identity we use today. When that name came, it honoured two men at once. The species name is terrelli, for Jay Terrell, the hotel keeper who first knelt in the shale and pulled the blunt face back into the light. It is a quiet kind of immortality. A man who never held a scientific post has his name spoken in laboratories and museums around the world, attached forever to one of the most formidable predators the oceans ever produced. The genus name honours a different man, Dunkleosteus. It carries the name of David Dunkel, a paleontologist at the Cleveland Museum of Natural History, whose work with these fossils earned him a place at the front of the name. Osteus comes from the Old Greek word for bone, so the full name, Dunkleosteus terrelli, reads almost like a small monument in Latin and Greek. Dunkel's bone, Terrell's fish, the scholar and the amateur, bound together in the single label that a sleepy listener might now recognise. Say it slowly to yourself if you like, Dunkleosteus terrelli. It is a heavy, rolling name for a heavy, rolling animal, and it is only fitting that a fish built like a fortress should carry a name that takes a moment to lift. Before we walk deeper into the century of digging that followed, let me say one small thing quietly, and then I will not interrupt again. If you are enjoying this slow walk through deep time, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. That is all. It helps more of these long, calm nights find the people who need them. Now, back to the rock, and the diggers who kept returning to it. Because the finding did not end with Terrell. It became a tradition. For generation after generation, collectors and museum crews returned to the Cleveland Shale, working those dark exposures wherever the land or the weather opened them. Every quarry cut, every eroding creek bank, every slope stripped bare of soil became a possible window into the Devonian. The armoured giant was rare, but the shale was generous to those who kept looking. And then, in the 1960s, the shale was opened on a scale no natural weather could match. Ohio was building a highway. Interstate 71 was being cut south through the land around Cleveland, and its path ran straight through Big Creek Valley. To lay a road, you must first move an enormous quantity of earth. Slopes were cut back, hillsides were sliced open, and in the process, fresh layers of Devonian black shale were exposed to the sky for the first time in hundreds of millions of years. Here was rock that no collector could otherwise have reached, laid bare in long, clean walls. The Cleveland Museum of Natural History understood what such an opening meant. Working together with the crews of the Ohio Department of Transportation, the museum organized salvage digs alongside the roadwork. As the earth was moved for the highway, trained eyes watched the freshly cut shale for the telltale gleam of fossil bone. It was a strange, quiet partnership. On one side, the practical work of building a modern road. On the other, the careful recovery of a predator that had died before the first tree grew a proper trunk. And the shale rewarded the effort. Those salvage digs pulled many new specimens out of the Creek Valley, adding armor plates and skull elements to the museum's collections, deepening what could be known about the animal. Try to hold the two timescales together in your mind, gently as you drift. A hillside is cut in an afternoon. The rock inside it is 360 million years old. One stroke of a machine reveals a slab of seafloor older than nearly everything that has ever walked on land. That is the ordinary magic of a place like the Cleveland Shale. The deep pass sits just beneath the surface, waiting only for something to open the ground. The digging did not stop at the edges of one valley, and the animal itself was not confined to Ohio. Though the Cleveland Shale gives the finest and most complete specimens, related material and members of this armoured family have been found much farther afield. Fossils tied to this giant and its close kin are known from Morocco, in North Africa, and from Belgium and Poland in Europe. The Devonian seas were wide, and the armoured fish ranged widely through them. That geography tells you something about the world it lived in. These were not isolated ponds. They were connected shallow seas spread across a very different arrangement of continents, warm and tropical and teeming. An animal built on this plan could turn up on rock that now sits an ocean apart. Ohio simply happens to hold the black shale that preserved it best, the still deep water that buried its dead with such unusual care. So the picture, by the middle of the 20th century, was this. A predator first noticed by a hotel keeper on a lakeshore in 1867. A formal name settled in 1956, honouring both that amateur and a museum scientist. A steady century of collecting crowned by the great salvage of the highway years, when a road cut through Big Creek Valley handed the museum a wealth of fresh bone, and a scattering of related finds across two other continents, hinting at how far these armoured hunters once ranged. But notice what all of that finding actually produced. Plates. Beautiful, heavy, interlocking plates of fossil bone, the armour of the head and the forward body. That is what weathered out of the cliffs, what emerged from the highway cuts, what filled the museum drawers. The shield, again and again. The fortress wall of the animal, preserved because it was the hardest, densest, most durable part of the body. And that is exactly where the mystery deepens rather than closes. Because armour is not an animal. Armour is what an animal wears. You can name every plate. You can measure each one, catalogue it, fit it against its neighbours like the pieces of a broken helmet. You can label the drawers and number the specimens and know precisely which cliff each fragment came from. And still you have not answered the first question a child would ask on seeing them. What did the whole creature look like? This is the strange gap at the heart of the science. For all the digging, for all the generosity of the Cleveland Shale, the rear body of this animal has never been found complete. Not once. The tail, the flanks, the shape behind the armoured head, all of it is soft-bodied by comparison, poorly armoured, easily lost. So while the shield survived in abundance, the body it protected slipped away into the mud and was not preserved whole. Everything anyone says about the full shape of this giant is inferred, reconstructed, argued from the plates, and from the anatomy of smaller relatives. For a long time, that gap was filled by a single confident image. Scale up the roughly 2-foot armoured head. Attach behind it a long, tapering shark-like body. Arrive at an animal perhaps 20 to 30 feet long, weighing well over a ton. A torpedo of muscle behind a battering shield. That is the reconstruction that filled museum halls and textbooks for the better part of a century. It felt settled. It felt like the truth the bones were telling. But bones tell only what you know how to ask them, and the plates that Terrell found, the plates that came out of Big Creek Valley, the plates in the museum drawers, still hold their answers close. They record with great precision the shape of the head, the fit of the armour, the terrible architecture of the jaws. What they do not directly record is the length of the tail or the breadth of the flanks. And so the size and the shape of the whole animal have become, in our own time, the subject of a genuine and unfinished scientific debate, which the later part of this long night will explore. Hold that uncertainty lightly as you rest. It is not a flaw in the science. It is the honest edge of it. We know this creature from its armour with extraordinary clarity, and we know its full body only by careful, contested inference. Both of those things are true at once, and a calm mind can hold them together without needing the tidier answer. For now, let the drawers close softly in your imagination. Let the highway cuts grass over. Let Jay Terrell walk back up his quiet lakeshore with a platter of ancient bone under his arm, not knowing that a museum scientist yet unborn would one day share the animal's name. The finding is done. The plates are gathered, named and numbered, laid out in ordered rows under museum light. And yet the gathering was never the point. Every one of those heavy plates was a piece of a machine, engineered by 100 million years of ocean predation to do one thing supremely well: to seize and to shear and to crush. The armour was not decoration. It was structure, load-bearing and precise, shaped around powerful muscle and a jaw mechanism unlike anything swimming today. To understand why a fish needed a head built like a fortress, you have to stop looking at the plates as objects in a drawer and start seeing them as parts of a living body. So the drawers are full, and the map of finds runs from a lakeshore in Sheffield Lake to a valley cut for a highway to the far shale of Morocco and Belgium and Poland. The naming is done, the honour divided between the amateur and the scholar. What remains is the harder and more wonderful work, the work of turning a pile of numbered armour back into an animal that once moved and hunted in a warm tropical sea. Follow the plates themselves, and the trail becomes a slow procession of hands. It begins on a lakeshore in 1867. Jay Terrell, a hotel owner near Sheffield Lake, Ohio, walked the Lake Erie cliffs with his son, and there in the black shale he found bone. Not a single bone. Plates, broad curved slabs the size of dinner platters, weathering out of the cliff face where the water and the frost had been prying at the rock for years. He did not know what he was holding. Nobody did. He called it the terrible fish, a name that was half guess and half awe, and the name stuck to it for decades before science had anything more careful to offer. Picture the position those plates were in. The shale here splits like wet cardboard, layer peeling from layer, and the armour lay flattened inside it, dark on dark, easy to walk past. You would have to know that a slight change in curve, a slight difference in sheen, meant bone and not stone. Terrell knew. He was an amateur, which in that century simply meant a person who looked closely at the ground for love rather than salary. What he pulled from that cliff was the front end of an animal, and only the front end, and that partial nature would shape everything that came after. Here is the first knot in the detective trail. The plates travelled. A fossil found on a lakeshore does not stay on the lakeshore. It goes into a drawer, then a crate, then a collection, and it passes from the hand that found it to hands that catalogue and compare. Over the decades that followed, more armour came out of the same shale belt across northern Ohio, and it flowed toward the institutions that could hold it. The specimens accumulated slowly, one weathered head shield at a time, until the drawers in Cleveland held a small crowd of these armoured fronts, each one a separate discovery, each one missing its back half. and that is worth pausing on, because it is the central difficulty of the whole hunt. You are trying to know an animal from its front door. The head and the thorax came sheathed in thick interlocking bone, and bone fossilizes willingly. The rest of the body did not wear armor in the same way, and much of the internal skeleton was cartilage, which rots and vanishes and leaves only impressions in the best of cases. So the record filled up with faces and shoulders, and almost nothing behind them. The people sorting these plates were reading a sentence that ended after its first few words, and being asked what the whole paragraph said. They did what careful people do with partial evidence. They measured. They compared plate to plate, noting how one head shield differed from another, how a jaw blade curved, how the bone thickened at a joint. They lined the specimens up and asked whether they were looking at one kind of creature or several. This is slow, unglamorous work, done under lamplight over trays of dark rock, and it went on for the better part of a lifetime before the animal got a proper name at all. That name did not arrive until 1956, which is nearly 90 years after Terrell stood on the cliff. Think of how many hands the plates had passed through in that stretch. The genus, when it finally came, was Dunkleosteus, and it honoured David Dunkel, a paleontologist at the Cleveland Museum of Natural History, who had given his attention to these Devonian fishes and to the collection that held them. The species name, terrelli, reached back across the decades to the man on the lakeshore, so the full name carries two people at once. Dunkel in front for the museum work that organised the animal into science, Terrell behind for the first eyes that ever saw it. There is a quiet justice in that arrangement, and it tells you something about how discovery actually works. The finder rarely names the find. The person who pulls bone from a cliff and the person who decides what that bone is are usually two different people separated by years, sometimes by generations. A name like Dunkleosteus terrelli is a small monument to that division of labour, the fieldwork and the desk work stitched together into a single label. You are meant to read both halves and remember that neither alone would have been enough. If you are drifting off as these names settle over you, let them. Before the trail goes further, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice, so the deep time keeps coming back to you on quiet nights. Then let the shale close over again, because the next chapter of the hunt arrives by accident. In the 1960s, machines cut a road through Big Creek Valley. Interstate 71 was pushed through northern Ohio, and where the roadbed sliced into the hillsides, it opened fresh layers of Devonian black shale to the air. This is the kind of exposure a fossil hunter dreams of and almost never gets. Natural cliffs weather slowly, revealing a plate here, a plate there, over years. A road cut lays open a wide, clean face of rock all at once, unweathered, full of whatever it has been holding since the seafloor settled. The Cleveland Museum of Natural History recognized the chance and coordinated salvage digs with the Ohio Department of Transportation, working the exposures while the rock was fresh and the digging was good. That salvage brought in many new specimens. It was a windfall born of pavement, a lucky accident of engineering that handed the museum more of the animal than patient lakeshore collecting had managed in decades. You can feel the difference in tempo. The lakeshore trail was slow, one frost-cracked plate at a time. The road cut was sudden. A whole valley of shale opened and worked before the highway sealed it under asphalt. Both are part of the same detective story, and both leaned on the same lucky chemistry of the rock. Because the Cleveland shale is not ordinary stone. It is black, fine-grained, and it formed on a seafloor starved of oxygen, a still dark mud where almost nothing lived to disturb a carcass that drifted down. Scavengers could not survive there. Currents did not stir it. So the dead settled into the ooze and stayed, pressed flat and preserved with unusual completeness. That is why so much of what is known about this animal comes from one formation in two Ohio counties, Cuyahoga and Lorain, in rock dated to roughly 362 to 361 million years ago. The same suffocating stillness that made the deep sea lifeless made it a nearly perfect keeper of the dead. Even so, the record kept its stubborn shape. More plates, more heads, more armoured shoulders, and still the back of the animal stayed missing. Complete rear body fossils of this fish have never been found. Not on the lakeshore, not in the road cut, not in any of the drawers the salvage filled. Every reconstruction of the body behind the armour is an inference, built from the head shield and from smaller relatives whose bodies happen to fossilise whole. The detectives had a face in high resolution and a body in shadow, and they had to reason across that gap with discipline, saying clearly where the bone ended and the guessing began. So they read the head like a document. Nearly half of the skull, it turns out, was cartilage rather than bone, including major joints and the places where muscle anchored. That soft framework almost never survives, and where it does survive, it survives as a faint impression, a ghost pressed into shale. To reconstruct the living animal, you have to notice those ghosts and trust them, filling the missing cartilage back into the armoured shell like water poured into a mould. It is painstaking, and it is honest work, and it is the opposite of certainty. And the trail did not stay in Ohio. The Cleveland Shale is the heart of the record, a place where the animal is best known and most completely preserved, but it is not the only place its armour has surfaced. Related material has come from Morocco, from Belgium, and from Poland, scattered plates on distant continents that speak to how widely these armoured fishes ranged across the Devonian seas. The find that began on one lakeshore in Ohio has echoes half a world away, in rock that was once other warm, shallow water under a different patch of that ancient globe. The heart is in Cleveland, the reach is intercontinental. Stand back and look at the whole hunt at once. It runs from an amateur on a cliff in 1867 to a museum name in 1956, through drawers and crates and lamplit comparison, into a highway salvage in the 1960s that a road crew opened by accident, and out finally to fragments in Morocco and Belgium and Poland. 90 years, many hands, and one persistent shortfall, a body that never turned up whole. The plates changed owners and changed institutions and changed continents, and at each step someone had to decide what a curved slab of ancient bone was actually telling them. The nickname became a name, the scattered armour became a species, the lakeshore find became a fixture in the collections that would puzzle over it for another lifetime and more. By the end of that long procession, the animal had a formal identity and a catalogue of plates, dated and located and honoured with two men's names. What it did not yet have was a body anyone could stand beside and measure. The armour had been gathered, the label had been written. Once the plates were named and numbered, the deeper question remained, the one the bones themselves were built to answer: what kind of body wore this armour and how was it made? Once the plates were named and numbered, the deeper question remained, the one the bones themselves were built to answer: what kind of body wore this armour and how was it made? Once the plates were named and numbered, the deeper question remained, the one the bones themselves were built to answer. What kind of body wore this armour, and how was it made? That is the question we walk through slowly now, in the dark, at the pace of settling silt. Set aside the maps and the shale cliffs for a while, come down instead to the level of the animal itself, and stand beside the great armoured head where it rests in the black Devonian mud, and look at it the way the bone lets you look. Begin with the shield. The most famous thing about Dunkleosteus terrelli is the casing that covered the front of it, a suit of thick interlocking bony plates that wrap the skull and the forward trunk in a single articulated shell. Picture 2 feet of solid bone laid across the head, roughly the width of a car tyre seen face on, and understand that this was not a thin veneer. These were structural plates, dense and heavy, fitted edge to edge like the panels of a hull. Paleontologists gave each one a name, but the animal knew them only as armour. The shell came in 2 connected regions, and the distinction matters. There was the head armour, the box of plates that enclosed the brain case, the eyes, and the jaws, and there was the thoracic armour, a second ring of plates that guarded the shoulders and the front of the body just behind the head. Between the two ran a hinge. The whole front of Dunkleosteus was, in effect, a hinged bony helmet joined to a hinged bony collar, and the joint between them let the head tip back while the trunk stayed anchored. Hold that image gently. It will matter later when the jaws begin to move. Run a hand across the surface of these plates, in imagination, and you would not feel smoothness. The outer bone carried a fine texture of ridges and tubercles, small raised bumps in the mineral, the kind of ornament common on placoderm armour. In life this may have been covered by skin, and the plates themselves grew and thickened as the animal aged, adding layers the way a slow tree adds rings. A young Dunkleosteus wore a thinner, lighter version of the same design. An old one wore a fortress. The armour was not a costume dropped over the body. It was living bone, laid down cell by cell across a lifetime. Now here is where the familiar picture starts to soften, and where the honest telling of this animal begins. Because for all its reputation as a creature of bone, Dunkleosteus was, beneath the shield, only half a skeleton of bone at all. Roughly half of the skull was not bone but cartilage, the same firm, flexible tissue that stiffens the tip of your own nose and the rim of your ear. The tank was armoured on the outside and gristle within. This is a strange thing to say about a fossil, because cartilage is almost never a thing a fossil keeps. Bone mineralizes and endures. Cartilage is softer, and in most animals it rots away in the first days after death, leaving a gap where solid anatomy used to be. So for a long time the cartilage half of Dunkleosteus was a blank, a region reconstructed by guesswork, filled in with careful assumption rather than direct evidence. The plates told you where the bone was. They could not, on their own, tell you the shape of what the bone was attached to. That blank has begun to fill. A study led by Russell Engelman at Case Western Reserve University, published in 2025 in the journal The Anatomical Record, worked from rare specimens in which the cartilage did not entirely vanish. In a few extraordinary fossils, the cartilage left an impression, a faint mould pressed into the surrounding matrix, or a ghost of its former surface preserved against the inner faces of the bony plates. From those impressions the team could read, for the first time in real detail, the shape of the parts that had always gone missing, and what they found was this. Nearly half the skull, including major jaw joints, and the sites where the great feeding muscles attached, was built of cartilage rather than bone. These were not minor structures. The jaw joint is the pivot on which the whole feeding apparatus swings, and the muscle attachment sites are where power enters the system. In Dunkleosteus, some of the most mechanically important architecture in the head was made of the tissue least likely to survive. The armour that made it famous was the durable minority. The working core of the animal was softer, and it had simply been lost from the record until someone learned how to see its shadow. There is a quiet lesson folded into that, and it is worth resting on for a moment in the dark. A fossil is not the animal. A fossil is the part of the animal that happened to endure, and endurance is not the same as importance. For more than a century, the story we told about Dunkleosteus was shaped by what fossilized easily, the heavy plates, the visible armour. The half that mattered most for how it lived was written in a material that keeps no record unless the conditions are almost perfect. In the still, oxygen-starved mud of the Cleveland Shale, just often enough the conditions were. That same 2025 study found something else, threaded through the cartilage and the bone together. Running through the head was a large bony channel, a passage that in life carried a major jaw muscle, and its shape resembled the arrangement seen in modern sharks and rays. It is some of the best fossil evidence yet for shark-like jaw musculature in one of these ancient armoured fish. Understand what that means for the picture in your mind. The muscle that closed these jaws was not some alien machinery unique to a vanished branch of life. It echoed the design still working today in the mouth of a living shark, hundreds of millions of years later, in the same warm seas of a different world. So the head takes shape now, more truly than the plates alone would give you. On the outside, an interlocking casing of thick bone, roughly 2 feet across, ridged and heavy, thickening with age. On the inside, a framework nearly half cartilage, carrying the pivots and the muscle anchors, invisible in most fossils and reconstructed here from faint impressions. And driving it, a broad channel for a powerful facial muscle shaped much like a shark's. Bone you could see, gristle you could not, and a muscle whose lineage runs unbroken to the present. That is the head of Dunkleosteus, half fortress and half ghost. Now to the mouth, and to the single most surprising absence in the whole animal. Dunkleosteus had no teeth. Not worn teeth, not few teeth, none. There was no row of enamelled points set in the jaw, nothing like the teeth of a shark or the teeth in your own head. Where the teeth should have been, the jawbones themselves rose up into blades. Take a moment with that, because it is easy to say and hard to truly picture. In most predators, the tooth is a separate structure, a specialized hard part seated in the jaw, replaced when it breaks, distinct from the bone that holds it. In Dunkleosteus, the cutting edge was the bone. The jaw plates grew upward and inward into sharp, bony ridges, and those ridges did the work that teeth do in other animals. The weapon was not mounted on the jaw. The weapon was the jaw, sharpened to an edge along its rim. There is a problem hidden in that design, and the animal solved it in a way that is genuinely elegant. A tooth, when it dulls, is shed and grown anew. A blade of solid bone cannot be replaced so casually. It is part of the jaw itself. Wear it down, and you blunt the very structure you feed with. A fixed bony edge should, over a lifetime of biting through shell and armour, grind itself smooth and useless. And yet Dunkleosteus fed on some of the hardest prey in its sea. Something kept the edges keen. The answer is that the blades sharpened themselves. The upper and lower plates were shaped so that when the mouth closed, they did not simply meet point to point. They slid past one another, edge grinding against edge, the way the two blades of a heavy shear pass and scrape as they close. Each bite wore a thin layer of bone from both edges at once, and in wearing them, renewed them. The grinding stripped away the dull surface and exposed fresh, sharp bone beneath. The very act that should have destroyed the edge was the act that maintained it. Sit with the economy of that. Every closing of the jaws was at the same time a cut and a sharpening. The prey was sheared, and the tool was honed in the same motion at no extra cost. There was no pause to replace a broken tooth, no soft interval while a new point grew in. The blades came out of every bite a little thinner and just as sharp, self-renewing for as long as there was bone to spend. A shear that wets its own edge each time it shuts. It is one of the cleaner solutions in the history of jaws, and it belonged to a fish that predates the first forests reaching their full height on the shore. We can read this history in the fossils themselves. On recovered jaw plates you can see the wear, the beveled and polished surfaces where the upper and lower edges dragged against each other bite after bite, year after year. The bone records its own use. An old plate carries the smoothed, angled facets of a lifetime of shearing, the physical memory of tens of thousands of closings, each one grinding a little more and staying keen. You are looking on that worn edge at the accumulated evidence of a way of eating that no living animal quite repeats. Step back now from the mouth to the whole shape of the beast, because the armour did more than protect, it set the animal apart. Around Dunkleosteus in the Cleveland Shale swam creatures built on a slimmer plan. There was Cladoselache, an early shark about 6 feet long, streamlined and supple, one of the best preserved early sharks we know, with impressions of its muscle and skin still readable in the rock. Beside that clean, tapering form, Dunkleosteus was something else entirely. Its head was a blunt armoured box, wide and deep and heavy at the front. Where the shark was a knife, the great placoderm was closer to a hammer. That tank-like head shield hints at the body behind it. An animal that carries 2 feet of dense bone across its skull and shoulders is not built for the same darting agility as a slender shark. The weight sits forward, at the front of the body in the plates and the jaws. Reconstruct the mechanics of that honestly, and you get an animal that was probably stout rather than sleek, powerful in the short strike rather than tireless in the chase, a heavyweight whose whole design pointed toward the front, toward the shield and the shearing mouth. The armour did not just guard the animal, it declared what kind of animal it was. And here we come to the honest edge of what anyone can say, a place where confidence has to stop. Because for all the fame of Dunkleosteus, for all the plates in museum drawers and the century of digs in the Ohio shale, no one has ever found a complete rear body of Dunkleosteus terrelli. Not one. The armoured head and forward trunk are known from many specimens. Behind the shield, where the body tapered back toward the tail, the fossils simply run out. That part of the animal did not preserve or has not yet been found. And so the true shape of the back half of Dunkleosteus is not a thing we have ever directly seen. This is not a small gap, and it deserves to be named plainly rather than smoothed over. Everything you have ever pictured behind the head of this fish, the length of it, the shape of its tail, the depth of its body, all of that is inference. It is reconstructed from smaller, more completely preserved relatives, other arthrodire placoderms whose whole bodies did survive, and from the anatomy of the head and thorax armour that we do have. The front of Dunkleosteus is evidence. The back of Dunkleosteus is a careful, reasoned guess, built from cousins. That gap is exactly why the size of this animal has been argued over for so long, and why the argument is still live. For most of the 20th century, the back half was drawn long and shark-like, and the whole fish was scaled up to something on the order of 20 to 33 feet, a monster of the open sea. Then, in 2023, Russell Engelman took the head-length proportions of those smaller, completely known relatives and applied them to the famous skull, and got a very different answer, an animal perhaps 11 to 13 feet long for a typical adult, shorter and far stouter than the old reconstructions. That revision is contested. It is treated as the newer view, not the settled one. Both figures still stand in the literature, and the disagreement itself is the honest state of the science. Notice what sits underneath that whole debate. It is the missing tail. If we had one good complete Dunkleosteus, head to tail fin, the size question would largely dissolve. We do not have one. So two careful readings of the same armoured head can still yield an animal 20 feet long or an animal half that, and neither can be proven wrong by a fossil that has never been dug up. When you next imagine this fish, hold its length loosely. The head is real and measured. The rest is our best reasoning stretched across an absence. Let that uncertainty settle over you gently rather than trouble you, because it is a kind of honesty the animal earns. We know the plates to the millimetre. We have learned to read the cartilage from its shadow. We can see on worn bone the self-sharpening bite recorded in polished facets, and we still cannot tell you for certain how long the creature was, because the part that would answer that has not survived. Both things are true at once. Precise where the bone endured, uncertain where it did not. That is what it is to know an animal only through what the mud chose to keep. So gather the pieces as they truly are in the dark before we move on. A shield of interlocking bony plates, roughly 2 feet across, casing the head and forward trunk, thickening across a lifetime. Beneath it, a skull nearly half cartilage, its jaw joints and muscle anchors reconstructed from rare impressions, carrying a broad channel for a shark-like closing muscle. In the mouth, no teeth at all, only bony blades that sharpened themselves by grinding edge against edge with every bite. A stout, front-heavy build unlike its slender neighbours. And behind the armoured shield, an honest blank, a back half known only through its smaller cousins. Every one of those features points the same direction. The heavy plates, hinged head to trunk. The powerful facial muscle in its bony channel. The self-renewing blades along the jaw. The forward-loaded tank-like frame. None of it was decoration, and none of it was accident. Each part was shaped by the same demand. the demand that runs through the whole animal like a current through the water it hunted in. It all converged on a single act, performed in a fraction of a second over and over across the life of the fish. The armour braced against it, the cartilage cushioned and pivoted for it, the muscle powered it, the blades delivered it, and you have not yet seen the half of it because the way those jaws open and shut is stranger and faster than anything we have said so far. And all of this armour and cartilage and self-sharpening bone existed to serve one motion, the closing of the jaws, which is where the real astonishment begins. And all of this armour and cartilage and self-sharpening bone existed to serve one motion, the closing of the jaws, which is where the real astonishment begins. Think of that head shield as a machine held in tension. Every plate you have followed, every seam of interlocking bone, every hidden reach of cartilage was arranged around a single hinge and a single purpose: to open, to close, to do it faster than your eye could ever register. Out there in the warm Devonian dark, the armour was the frame, the blades were the tools, but the mechanism between them, the thing that turned a wall of bone into a weapon, was a piece of engineering so elegant that people still study it to understand how fast a jaw can possibly move. Let that settle for a moment before we take it apart. You are floating in a shallow tropical sea, somewhere over what will one day be northern Ohio, roughly 360 million years ago. The water is warm, the colour of weak tea in the upper light, then blackening as it deepens. A shape drifts at the edge of vision, and then, in less time than it takes you to notice it at all, the shape has fed. The prey is simply gone, halved, sinking. That is the effect we're trying to explain. Not the size, not the armour, but the speed and the force of the bite itself. And if the mechanics of that bite hold you the way they hold the people who measure such things, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in podcast app of choice, and let the rest of this ancient world unfold around you slowly. Now, to the mechanism. In 2007, two researchers named Philip Anderson and Mark Westneat published a study in the journal Biology Letters that reframed how we think about this animal entirely. They did not just weigh the armour or measure the blades, they modelled the skull as a machine. Specifically, they treated it as a 4-bar linkage, and that phrase deserves a slow, patient unpacking, because it is the heart of everything. A 4-bar linkage is one of the oldest ideas in mechanical design. Picture 4 rigid rods connected end to end by 4 pivots, forming a loop. Hold one rod still and move another, and the whole loop responds in a fixed, predictable way. Turn one bar a little, and a distant bar swings much farther, or much faster, depending on how you set the lengths. It is the logic behind a folding chair, a car hood, a swinging gate. Motion in one place, amplified and redirected somewhere else. You have used dozens of them today without ever naming them. In Dunkleosteus, 4 bars were not steel. They were bone, 4 linked skeletal elements, joined at their pivots, wrapped inside that armoured head. When the animal fired the muscles that swung its skull upward and dropped its lower jaw, it was not simply hinging open a mouth, it was driving a linkage. One input motion, at one joint, rippled through the connected bars and threw the jaws apart far faster than the muscle alone could have managed. The mechanism multiplied the speed, the bone did the amplifying, and the number that came out of that model is the one that stops people. Big gape. The fully open mouth reached in as little as 20 milliseconds, 20 thousandths of a single second. Let me give you something to hold that against. A human eye blink takes somewhere between 100 and 400 milliseconds. So this fish could fling its entire armoured jaw wide open in roughly 1/10 of the time it takes you to blink or less. The mouth was open before the light of the movement could finish reaching a watching eye. The full cycle, open and then closed again, ran to something like 50 to 60 milliseconds, still faster than that blink. In the span of a single unhurried heartbeat of your own, resting, half asleep, this animal could have opened, seized, and sheared. Among fish, that places it near the very top of everything ever measured for raw jaw speed. Not the fastest small fish flicking at plankton, but astonishing for a predator built like a bank vault, an animal whose head alone could weigh as much as a grown person. Sit with the strangeness of that pairing. Armour and speed do not usually travel together. Weight is the enemy of quickness. A thing that heavy should be slow, and that is exactly what your instinct tells you when you imagine a wall of bone in the water. But the linkage cheated that expectation. It let a massive reinforced skull behave for 20 milliseconds, like something light and sudden. The mass was in the frame, the speed was in the geometry. That is the trick the 4-bar linkage performed over and over every time this animal fed. Now understand what the speed actually brought. When you open a mouth that fast underwater, you do more than clear a path for the blades. You drop the pressure inside the mouth almost instantly. Water rushes in to fill the sudden void, and it carries loose things with it. Small fish, fragments, prey, that thought, for a fraction of a second that it had a fraction of a second. The mouth becomes not just a trap but a kind of intake. We will come back to that idea because it is genuinely debated, and honesty about the debate is part of the pleasure here. But hold the image for now. The gape was not slow enough to flee. The gape was the ambush. Then the jaws close. And this is where the second number lives, the one about force rather than speed. Anderson and Westneat, in that paper and in a fuller follow-up in the journal Paleobiology in 2009, did not just clock the motion. They calculated how hard the closed jaws could push, and the figures they produced put this Devonian fish in company you would not expect. At the front of the jaw, near the tip where the biting edges met, their model estimated a bite force of roughly 4,400 newtons. Toward the back, at the rear plates, where the leverage was greatest. In the largest individuals, the force climbed higher still, into a range of about 5,300 to more than 7,400 newtons. Newtons are a unit of force, and if the word feels abstract, anchor it in something you can feel. Very roughly, it takes about 4.5 newtons to lift 1 pound against gravity. So a bite of 7,000 newtons is, in that loose translation, comparable to the weight of well over 1,500 pounds bearing down at a point. Imagine a small car pressing its full weight on the edge of a blade. Now imagine that blade is bone, self-sharpened, and that the pressure arrives in less time than a blink. That is the closing half of the bite. Those numbers matter most in the company they keep. Bite forces in that range rival the estimates calculated for large alligators. The modern animals we think of as the gold standard for a crushing bite. A big alligator clamps down on turtle shells and bone with a force we treat as almost mythic, and this ancient fish sat right there beside it, or in the same neighbourhood. And at the upper end of the estimates it begins to approach the figures modelled for Tyrannosaurus rex, an animal that would not exist for another 130 million years, an animal separated from this fish by a gulf of time longer than the one that separates the tyrant from you. Hold that comparison gently, because it is doing something rare. When you think of the most powerful bite in Earth's history, your mind reaches for the tyrant lizard, jaws lined with railroad spikes. But long before any dinosaur drew breath, in a warm sea with no name, a fish with no teeth at all had already engineered a bite in the same league. The record for terrible force was set and nearly matched before the land vertebrates had properly figured out how to walk. That is the quiet astonishment this segment is built around. Not that the tyrant was strong, but that the tyrant was late. Now we have to be careful, because there is a more dramatic number that circulates, and part of being a trustworthy companion in the dark is telling you plainly where a figure comes from. You may have heard that Dunkleosteus could concentrate something like 80,000 pounds per square inch at the very tip of its blade. It is a startling figure, and it gets repeated everywhere, and it is worth understanding honestly. Force and pressure are not the same thing, and that difference is the whole story of that number. Force is the total push. Pressure is that push divided by the area it lands on. Press your whole hand flat against a table and you feel almost nothing. Press the same effort through the point of a needle and you draw blood. Same force, wildly different pressure because the area shrank. Now, the biting edges of this fish were not needles, but they were edges, narrow lines of self-sharpening bone. When you take a bite force in the thousands of newtons and funnel it down onto the thinnest sliver of a blade tip, the pressure at that tiny point soars into enormous numbers. That is where the 80,000 pounds per square inch comes from. It is a calculation about the tip, not the whole jaw. And here is the honest part. That specific pressure figure traces back to press coverage and popular summaries built around the research, not to a single controlled, peer-reviewed measurement of the pressure at the blade tip. The careful, published biomechanics gives you the forces, the newtons, the speeds. The 80,000 psi is a widely repeated estimate, a headline that grew up alongside the real work. It is probably not wrong in spirit. A concentrated point on a self-sharpening edge really would generate ferocious pressure. But you should carry it as a popularized figure, a rough and vivid illustration, and not as a settled, measured fact filed beside the newtons. When you hear it quoted as gospel, you will now know exactly what kind of number it is. That distinction between what was modelled and what was merely printed is the difference between science and a good story, and both have their place, as long as you know which one you're holding. So the honest core, the part you can lean your full weight on, is this. Extraordinarily fast with peak gape in around 20 milliseconds. Extraordinarily strong, with modelled bite forces in the thousands of newtons, rivaling large alligators and approaching the tyrant lizard. A machine of bone that opened faster than sight and closed with the weight of a car on a blade. That much is careful, published, and repeatable. The rest is embellishment, and we can enjoy it as such. Now to the debate I promised you, because it is one of the more beautiful open questions about this animal, and it turns entirely on that fast expanding gape. Some researchers have proposed that Dunkleosteus did not simply bite. They suggest it fed, at least in part, by suction. The reasoning follows directly from the speed. When the jaws snapped open in 20 milliseconds, the volume inside the mouth expanded violently, and that sudden expansion would have dropped the internal pressure and pulled a rush of water inward. Many living fish feed exactly this way, flaring their mouths to inhale prey along with a gulp of water, a technique so common in modern seas that it is almost the default way a fish eats. If this armoured giant could expand its mouth that fast, the argument goes, it could have used the same physics, drawing struggling prey toward the waiting blades rather than chasing every meal down by brute pursuit. The gape would be both the opening and the lure. It is an elegant idea and it fits the machinery, but it is genuinely questioned, and the objections are worth sitting inside because they show you how paleontologists argue with the physical world. Suction feeding works beautifully at small scale. A little fish flares a little mouth and the surrounding water responds quickly and cleanly. But scale the mouth up to something enormous, wrap it in heavy interlocking armour and set it in the open water of a shelf sea, and the physics grows uncooperative. Moving that much water fast enough to generate real useful suction through an armoured aperture in an animal this large may simply not be mechanically plausible. The mouth might expand quickly, yes, but whether that expansion could actually inhale substantial prey, rather than just admit a modest inrush, is far from settled. So the feeding mode sits unresolved, and I will not pretend for you that it is decided. On one side, pure bite and shear. The animal closes the distance, opens those linked jaws, and severs its prey with edges of self-sharpening bone, the gape serving mainly to clear the blades and startle the target. On the other side, suction assist, where the rapid expansion actively helps draw prey inward before the blades come down. The likeliest truth may lie somewhere between, a bite-dominated animal that got some incidental inrush from the speed of its gape, without relying on suction the way a smaller fish would. What you should carry away is not a verdict, but the shape of the uncertainty, a jaw that fast could in principle pull. Whether it truly did, at that size, in that armour, is one of the questions this fish has not yet finished answering. There is a newer thread worth adding here, because the science kept moving. A study led by Russell Engelman at Case Western Reserve University, published in 2025, reconstructed the full musculoskeletal anatomy of the jaws in unusual detail, and it found a large bony channel that would have carried a facial jaw muscle strikingly like the arrangement seen in modern sharks and rays. That is some of the best fossil evidence yet that this ancient armoured fish carried shark-like jaw musculature, which tells you something about how the bite was powered and controlled, and hints that the machinery driving that 4-bar linkage was more sophisticated than a simple hinge. The picture keeps sharpening. The animal keeps giving up its secret slowly. Let us pull all of this back down to the seafloor, because numbers are cold and this animal was not. I want you to feel what the speed and the force meant in practice, out in that warm, silent, tea-coloured water. Imagine you could stand on that Devonian bottom, in the slanting light of the upper sea, and watch a hunt in real time. You would fail. Not because it happened far away, but because it happened too fast to pass. The prey, perhaps a smaller placoderm, perhaps an early shark drifting a little too close, would be swimming, and then it would be in 2 pieces. The intervening event, the opening and closing of that armoured mouth, would occupy less time than a single blink. A motion so brief your nervous system would smear it into nothing. You would see a before, you would see an after. The bite itself would live in the gap your eyes could not cover. That is the raw physics of shearing prey. Speed removes the possibility of escape, because escape requires reaction time, and there was none to be had. Force removes the possibility of resistance, because armour and shell and cartilage all yield when a small car's worth of pressure arrives on a self-sharpening edge. Together they made a bite that was less a struggle than a verdict. The prey did not fight and lose. The prey was simply resolved, cut, in 20 to 60 milliseconds, by a machine that had already moved on. And notice what the whole animal has become. Now that you understand the jaws, every feature you followed earlier turns out to have been in service of this instant. The interlocking armour braced the skull against the shock of that force, so the head did not tear itself apart from the inside each time it fed. The half-cartilage skeleton kept the whole structure light enough that the linkage could fling it fast. The self-sharpening blades meant the cutting edge was renewed with every closure, never dulling, never needing replacement, honed by the very act of biting. The 4 bars of bone converted ordinary muscle into extraordinary speed. It is all one system. Pull any thread, and the others answer. The armour, the cartilage, the blades, the linkage, all of it converging on a single, repeatable 20-millisecond event. Take one slow breath here, in the dark, and hold the completeness of it. This was not a creature that happened to have a strong bite. This was a bite that had grown a creature around itself, an entire armoured body organised, from the seams of its plates to the hollows for its muscles, around the closing of 2 blades of bone. Nature does not often build a thing so single-minded. When it does, the result tends to sit at the top of its world for a very long time, and this one did for tens of millions of years, in seas that would leave no other trace but black shale and the memory of that jaw. You began this segment with an image of a shape at the edge of vision, and prey that was simply gone. Now you know the mechanism behind the vanishing. A 4-bar linkage of bone, a gape in 20 milliseconds, a closing force to rival an alligator and shadow the tyrant lizard, delivered on edges that sharpened themselves, a bite that opened faster than you could see and closed harder than almost anything alive before it. That is what was drifting through the warm Devonian water 360 million years before anyone would give it a name. But a mechanism, however perfect, is only half an answer. A jaw exists to meet something. All this speed, all this force, all this careful convergence of bone and cartilage and blade was aimed outward, at other bodies, at other lives moving through the same warm sea. The tool implies the target, and so the question the bite leaves behind is not how it worked, but what it worked upon, what swam close enough to be resolved, what was strong enough, or shelled enough, or fast enough to matter. To answer that, you have to leave the machinery of the skull and go looking for the creatures that shared this water, the ammonoids and the early sharks and the other armoured giants, the whole crowded community that this bite was built to feed within. Picture, for a moment, how anyone could know the speed of a bite from an animal that died before the first forest fully greened the shore. No one timed it. No stopwatch, no living jaw to watch. What you have instead is bone, and the patient logic that lets bone confess how it once moved. The number you may have heard, that peak gape in as little as 20 milliseconds, is not a memory. It is a reconstruction, and the way it was built is worth walking through slowly. Start with a simple, almost humble idea from engineering. It is called a 4-bar linkage. Imagine 4 rigid rods joined end to end in a loop, connected by 4 pivots, so the whole thing can flex but never come apart. Push on one bar, and the others must move in a fixed, predictable way. A screen door closer is a 4-bar linkage. So is the mechanism in many cabinet hinges. The beauty of it is that the motion is determined entirely by the lengths of the bars and the placement of the joints. Set those, and the path is locked. Nothing is left to guess. Fish skulls, it turns out, are full of these loops. A fish head is not one solid mask. It is a cluster of bony plates linked at movable joints, and when the right muscle pulls, several plates rotate together in a chain. In Dunkleosteus, the skull and the upper jaw and the lower jaw and the joint at the back of the head form exactly this kind of coupled system. The head shield could tilt up while the lower jaw dropped down, both at once, opening a far wider gape than either motion could manage alone. That double swing is the signature of a linkage doing its quiet work. So in 2007, 2 researchers, Philip Anderson and Mark Westnett, took that principle and pressed it onto the fossil. They measured a well-preserved skull. They mapped where the plates met, where the joints sat, how long each bony bar ran between one pivot and the next. Then they modelled the head as a set of connected 4-bar linkages, feeding in those lengths and angles the way you might feed dimensions into a drawing. Once the geometry was fixed, the physics followed. The model could predict how fast the jaws swung open when the input muscles fired, and how the whole cycle played out from rest to full gape and back to a closed sheared bite. That is where the striking figures came from. Peak gape in as little as 20 milliseconds, a full bite cycle, open and snap shut, in 50 to 60 milliseconds. To feel how brief that is, think of the blink of your own eye, which takes something over 100 milliseconds from start to finish. This fish could open and close its mouth in half a blink or less. In a warm, murky sea where prey darted at the edge of sight, that speed was its own kind of weapon. Slow jaws let a meal escape. These jaws did not give the meal time to decide. Now hold the honesty of it in mind. The 20 milliseconds is not a stopwatch reading. It is what the geometry predicts if the bars are the lengths measured and the muscles pulled with the assumed force. Change the measurement of one plate or the placement of one joint, and the predicted speed shifts a little. The model is only as firm as the fossil it was fitted to, and every input carries a small cloud of uncertainty around it. Good modelling does not hide that cloud. It carries it forward into the answer. The bite force numbers work the same patient way, and they deserve the same care. You will see them quoted crisply, thousands of newtons. No one ever measured them. They are calculated. The recipe is straightforward in principle. You estimate the size of the jaw muscles from the space in the skull where they anchored. You estimate how hard muscle of that cross-section can pull. Then you treat the lower jaw as a lever, with the joint as the fulcrum, and you work out how much of that muscular pull becomes force at the biting edge. Where you press matters enormously. A lever gives more force near the hinge and less at the tip, the same way a nutcracker crushes hardest close to its pivot. That is why the numbers come as a range rather than a single figure. The peak simulated forces landed somewhere around 4,400 newtons near the front of the jaw, and climbed higher toward the rear plates, past 5,000 and towards 7,400 newtons and beyond in the larger individuals modelled. To give that weight a body, 7,400 newtons is roughly the force of well over 1,600 pounds bearing down at a point. That places Dunkleosteus among the hardest biting fish ever calculated, in the company of a large crocodilians, and reaching toward the estimates made for far later giants on land. But notice how many words carry conditions, depending on location on the jaw, depending on assumed body size. Those are not hedges dropped in for modesty. They are the actual switches that move the answer. Body size is the quiet giant behind all of it. A bigger animal has bigger muscles and longer levers, and the force scales up accordingly. So the bite force estimate is tied, hand in glove, to how large you think the fish was, and that has become one of the liveliest questions around this creature. For decades, the popular figures ran long, 20 to 33 feet, built by scaling the armoured head to a slender, shark-shaped body. More recently, a reanalysis argued for something shorter and stouter, perhaps 11 to 13 feet for a typical adult, drawn from the proportions of smaller relatives whose whole bodies are known. That debate is not settled, and it ripples straight into the biomechanics. Shrink the assumed animal, and you nudge the assumed muscle, and the force estimate breathes in and out with it. When you read a single bold number, remember it rests on a chain of choices upstream. You may also have met a far more dramatic figure, a pressure at the blade tip quoted in the tens of thousands of pounds per square inch. Treat that one gently. It traces back to press coverage and popular summaries rather than a single controlled measurement, and it describes pressure, force concentrated onto a tiny edge, which is a different quantity from the total bite force the models compute. Concentrate any strong bite onto a thin enough blade and the pressure at that edge climbs steeply, because pressure is force divided by area. It is not wrong to be impressed. It is only worth knowing which numbers came from careful modelling and which came from the retelling. The work did not stop with the linkage. In 2025, a team led by Russell Engelman at Case Western Reserve University went back to the skull to rebuild the soft machinery, the muscles and their attachments, not just the bony bars. Much of what drives a jaw is invisible in most fossils, because muscle rots and cartilage rarely lasts, and nearly half of this skull was cartilage rather than bone to begin with. But muscles leave marks where they anchor. Where a large muscle pulled, the bone often carries a channel or a scar shaped by that pull, and the team found a large bony channel that would have carried a major facial jaw muscle, one strikingly similar to the arrangement seen in modern sharks and rays. Sit with what that means. It is some of the best fossil evidence yet that an armoured fish from before the age of dinosaurs already carried jaw musculature built along the same lines as living sharks. The linkage told you how the bones could swing. This reconstruction begins to show you the engine that swung them, inferred not from imagination, but from the shape the muscle left behind in the bone. It is a second, independent window onto the same closing jaw, and when two different methods, the geometry of the plates and the anatomy of the muscle scars, point toward the same fast, powerful bite, the picture grows steadier. Still, every figure here wears an error bar, and learning to read that honestly is the real gift of the exercise. A modelled number is a sentence with conditions folded inside it. 20 milliseconds if the joints sat where measured, 7,400 newtons if the animal was that large and the muscle pulled that hard. The range is not weakness. The range is where the truthfulness lives, because it tells you how much the answer would move if a fresh fossil corrected one assumption. A single confident number with no range around it is often the less trustworthy claim, not the more. There are open questions the models cannot yet close. Whether those fast-opening jaws also generated suction, drawing water and prey inward the way many modern fish feed, is still argued, and some doubt it was mechanically workable for an animal so large and so armoured in open water. The exact body size stays contested. The precise muscle forces will shift as the size question settles. None of that undoes the core finding. It simply keeps the honest edges visible, which is what a good reconstruction should do. What survives all the caveats is a machine of genuine elegance. 4 linked bars of bone driven by a shark-like muscle whose channel still marks the skull, swinging a head shield and a lower jaw apart and back together in less time than it takes you to blink, closing with a force measured in the thousands of newtons wherever the blades met. Every part of that sentence was recovered from stone and reasoning, carefully, with the uncertainty carried along rather than swept aside. A bite like that was never built for show, and to understand what it fed upon you have to follow this fish out into its crowded tropical sea. A bite like that was never built for show, and to understand what it fed upon you have to follow this fish out into its crowded tropical sea. A bite like that was never built for show, and to understand what it fed upon you have to follow this fish out into its crowded tropical sea. The water is warm here, somewhere in the 70s and 80s on the Fahrenheit scale. That is the temperature of an equatorial shelf sea in a world with no permanent polar ice, and for most of the Devonian there is none. Sunlight slants down through the clear upper layers, then softens, then thins toward a darkness that never quite lifts. This is the Late Devonian, roughly 360 million years ago, a stretch of time so deep it sits about 130 million years before the first Tyrannosaurus will ever draw breath. Picture the land that will one day be Ohio resting south of the equator, drowned under this quiet, shining shelf. Somewhere in it moves Dunkleosteus terrelli, its head and shoulders sheathed in interlocking bone. Before we go further into how it lived and how it died, let this pace stay slow. There is no hurry in deep time, and there is no hurry here. Begin with the young, because every armoured giant starts small. A juvenile Dunkleosteus is not a scaled-down tank so much as a lean, quick hunter still growing into its plating. Its jaws are not yet the crushing machines they will become, so the small ones almost certainly took small things. Soft-bodied prey drifting in the water column, little fish that flickered past in loose schools, worm-like animals and the tender unshelled bodies that leave almost no trace in the rock. A young placoderm needs speed and precision more than raw force, and its diet reflects that. It eats what it can catch and swallow whole, or shear with a jaw that has not yet learned its full strength. As the animal grows, the menu changes with it. The blade plates that serve in place of teeth thicken and lengthen. Remember, this fish has no true teeth at all. Instead, only plates along the jaw form sharp cutting edges, and those edges are self-sharpening. They wear against each other with every bite, grinding themselves to a fresh point the way a pair of shears keeps its edge through use. An old adult carries jaws honed by a lifetime of closing on hard things, and hard things are what the adult can now attack. The thick-shelled ammonoids that drift and jet through the middle water become fair prey. These are coiled cephalopods, cousins of the ammonites that will later swarm the seas of the dinosaurs, and their shells are built to keep soft predators out. A crushing bite ignores that defense. Where a shark would gnaw and fail, Dunkleosteus simply closes and the shell gives way. The biomechanical models put the force at the front of the jaw near 4,400 newtons, and higher still, past 5,000 and towards 7,000 newtons, at the rear plates in the largest individuals. That is force in the range calculated for large alligators, closing on a coiled shell no thicker than your thumb. It is not only shells. An adult Dunkleosteus could turn on other armoured fish, on other placoderms sheathed in their own bone. Its bite was one of the few weapons in that sea capable of defeating armour with armour, of biting through the very defence that kept most predators away. Think of the diet as a slow climb up the hardness of the world. As a juvenile, you take the soft and the small. As you grow, you graduate to the shelled, the plated, the things nothing else can open. There is a strangeness in imagining a single animal that lives across such different worlds. The young one hides and darts and snaps at drifting softness. The old one cruises with a head like a wall and opens whatever it chooses. Same species, same lineage of bone, two entirely different ways of feeding, separated only by years of growth. Growth in Dunkleosteus is written into its plates the way it is written into most fish, in layers laid down over a life. The armour thickens. The skull, in a full adult, spans roughly 2 feet from front to back, a shield of interlocking bone over head and thorax. Behind it the body remains uncertain to us, and we will come to why. But the head grows into a thing that fears very little in its own sea. Very little, except perhaps its own kind. Here the record turns dark and personal. Paleontologists studying the armour plates of Dunkleosteus have found something unsettling on some of them. Scrape marks, puncture marks, gouges in the bone whose spacing and shape match the bite plates of Dunkleosteus itself. In plain terms, the armour of one of these fish sometimes carries the tooth blade signature of another. The most direct reading of that evidence is cannibalism. These animals, at least on occasion, bit one another, and the biggest of them may have preyed on their own. Hold that idea gently, because the science holds it gently too. A bite mark on old bone does not always tell you the whole encounter. It might record a killing. It might record scavenging on an animal already dead. It might record a fight over territory or a mate that left the loser wounded but alive. What the marks establish is contact, jaw against armour, one Dunkleosteus closing on the plating of another with enough force to score the bone. Occasional cannibalism is the phrase the researchers reach for, and occasional is the honest word. Not a habit, not a rule. A behaviour that happened and left its fingerprints pressed into the fossils we now hold. It fits, in a grim way, with everything else about this animal. In a sea where the hardest prey was other armoured fish, the hardest prey of all was simply a smaller version of yourself. A large adult meeting a half-grown juvenile might have seen nothing but food inside a familiar shape. So the young had reason to stay away from the old, to hunt different prey in different water, to keep their soft, growing bodies out of reach of jaws that could crush a shell without slowing down. The diet shift across a lifetime was not only about what the jaws could handle. It may also have been about survival, about small Dunkleosteus learning early to avoid the shadow of the large. Now let the eye pull back from this one fish and take in the neighbourhood it lived in, because Dunkleosteus did not rule an empty sea. The Devonian is called the Age of Fishes for a reason. The water around you teems with jawless fish and early-jawed fish, with drifting ammonoids, with the looming tank-like silhouettes of other placoderms, and moving through it, sleek where Dunkleosteus is heavy, comes an early shark named Cladoselache. Cladoselache is small by the standard of the armoured giants, roughly 6 feet long, about the length of a tall grown person laid head to heel. It is streamlined where Dunkleosteus is blunt, built like a torpedo, all smooth muscle and fin, one of the earliest sharks we know in real detail. And we know it in remarkable detail, because the same rocks that hold Dunkleosteus hold Cladoselache too, and they hold it beautifully. Some of the best preserved early shark fossils in the world come from this place. Impressions of muscle, impressions of skin, the soft outline of a body that in almost any other setting would have vanished without a trace. Best of all, some Cladoselache fossils preserve the last meal still sitting in the gut. When you can read a fossil animal's stomach contents, you're no longer guessing at its life, you're looking straight at it. And what these early sharks had eaten was small fish, cephalopods, and shrimp-like arthropods, little jointed swimmers darting through the same water. Picture that. A 6-foot shark, 360 million years old, and inside it the fish it chased, the soft-bodied squid cousins it snapped up, the tiny armoured swimmers it strained from the current. That is not reconstruction. That is a preserved fact, a meal frozen mid-digestion in stone. Cladoselache shows you the other way to make a living in this sea, not armour and crushing force, but speed and agility. It hunted the same small prey a young Dunkleosteus hunted, and it likely fled the same large predators. Between the heavy placoderms above and the quick sharks below, the middle water was a busy, layered place, each animal fitted to its own slice of the food and its own way of moving. And then there is the giant in the room, the one contemporary that rivaled Dunkleosteus for sheer size. Its name is Titanichthys, and its story is one of the strangest turns in the whole cast. Titanichthys was another arthrodire, another armoured placoderm of the Late Devonian, and by the older reconstructions it was enormous, estimated at 23 to 25 feet, matching or even exceeding Dunkleosteus in the traditional picture. That same 2023 reassessment that shrank Dunkleosteus revised Titanichthys downward too, towards something closer to 13.5 feet, similar in scale to the newly compact Dunkleosteus. So the two giants may have stood shoulder to shoulder in size, whatever their true measurements were. Both wore the armoured head shield of their group. Both were among the largest animals in their world. But here is the twist. Titanichthys carried none of Dunkleosteus's weapons. Its lower jaw was narrow, it was toothless, like all placoderms, and unlike Dunkleosteus it lacked the cutting edges entirely. No blades, no shearing plates, no crushing surfaces. A jaw built for force would never look like that. So what was such a giant doing with a mouth that could not bite hard? A 2020 study proposed an answer that reframes the animal completely. Titanichthys, the researchers argued, was a suspension feeder, a filter feeder, an animal that opened its great mouth and strained small prey from the open water. Schools of little fish, clouds of drifting zooplankton, the living soup of the sea, gathered by the mouthful and sieved from the current. If that reading holds, Titanichthys stands among the earliest large-bodied vertebrate filter feeders ever known, an ancient forerunner of the way a modern whale shark or a basking shark makes its quiet, enormous living. Sit with that contrast for a moment, because it tells you how full this sea really was. Two giant armoured fish, roughly the same length, sharing the same water. One with a bite among the strongest of any fish that ever lived, closing on shells and armour and its own kind, the other gliding open-mouthed through clouds of the smallest prey, taking nothing by force and everything by patience. The same body plan, the same armoured heritage pointed at opposite ends of the food web. The Devonian sea was wide enough to hold them both. Now let the scene settle and ask the quieter question. How do we know any of this at all? How does the last meal of a shark, or the bite mark on a giant's armour, or the narrow toothless jaw of a filter feeder survive across 360 million years to reach us? The answer lies in the mud itself, in the very floor of this sea. Beneath the warm, sunlit upper water, the bottom here was another world. Dark, still, starved of oxygen. The fine sediment that settled there particle by particle, built up into a black fine-grained mud that would one day harden into the Cleveland Shale of northern Ohio, rock dated to roughly 362 to 361 million years old. And the chemistry of that mud is the reason this whole lost world can be read. Oxygen is what drives decay. Oxygen feeds the scavengers, the bacteria, the burrowing animals that would normally tear a carcass apart and scatter it before it could ever become stone. On this sea floor there was almost no oxygen. The deep water lay heavy and unmoving, and nothing could live down in it for long. A body that sank into that mud sank into a place where the usual destroyers could not follow. No crabs to pick it clean, no worms to churn it under, no current to roll the bones apart, only silence and cold, and the slow rain of more sediment settling over the top. That is why so much of what we know about Dunkleosteus comes from this single formation. The anoxic mud was a killing floor for scavengers and a cradle for preservation. It held the armoured heads intact. It preserved, in the case of Cladoselache, the delicate outlines of muscle and skin, and the meal still lying in the gut. It kept the bite-scarred plates of one Dunkleosteus close enough to read the marks of another. Even the cartilage tells its story. Nearly half of the Dunkleosteus skull was cartilage rather than bone, the jaw joints, the muscle anchors, tissue that almost never survives, and yet impressions of it linger in these rocks where a gentler grave would have lost it entirely. Think of what that means for a moment as you lie there in the dark. The clearest window we have onto one of the first great predators of the vertebrate world exists, because the bottom of its sea was a place where almost nothing could live. Death preserved it. Stillness kept it. The very lifelessness of that deep mud is what carried these animals forward to us, unbroken, across an ocean of time. So follow one carcass down. An old Dunkleosteus reaches the end of its long life somewhere in the upper water, and its heavy armoured head begins to sink. Down through the warm-lit layers it goes, past the drifting ammonoids, past the quick shapes of sharks, past the last reach of the sun. Below a certain depth the light gives out, the colour drains, and the world turns to black. The body settles onto the soft anoxic mud and presses in. There it stays. The soft parts that remain slowly go, but the great shield of bone holds, and the sediment keeps falling, grain by patient grain, sealing it away. That is the record we read. Not a museum arranged for us, but the ordinary deaths of ordinary animals dropped into a mud that happened to remember. Every plate on display, every reconstruction argued over, every bite force modelled, and every meal identified, all of it traces back to bodies that fell into the dark and were kept. The sea was the recorder, the lifeless floor was the page, and the ink was time. Let the picture hold there, whole and intact, before the world we have been standing in begins to change. Take one slow, easy breath, and stay in this sea a little longer. Picture the surface far above the black mud, lit and warm and alive. Ammonoids pulse through the middle water. Cladoselache cuts its quick, hungry arcs. Titanichthys drifts open-mouthed through drifting clouds of the small, and through all of it moves Dunkleosteus, blade-jawed and armoured, the crushing centre of a world that has settled into a long, stable balance. On the distant shores, out of sight of these deep fish, the first true forests are rising, archaeopterous trees with woody trunks more than a yard thick, a low green skyline over stony ground where nothing yet walks. The sea below them stays busy and full, predator and prey, giant and swift, hard shell and soft body, each fitted into its place. This balance was not a single quiet afternoon. It lasted. The world of the armoured fish was not a brief experiment, but a long and successful reign. And Dunkleosteus and its neighbours held their sea across a span of time longer than most human minds can truly hold. Kingdoms of armour rose and fed and sank into the mud generation after generation, and the sunlit water above the anoxic dark stayed crowded and warm. Nothing about that world announced that it would ever end. The predators were superbly built. The prey was abundant. The mud kept its patient records, and the forests thickened on the far shores, and the great filter feeder and the crushing giant went on making their opposite livings in the same warm shelf. The armoured fish had not merely survived the Devonian, they had defined it. This was their age, and it did not feel like an ending. But every stable world sits on conditions it does not control, and the conditions here would not hold forever. The warmth that filled these seas, the chemistry of that deep, breathless mud, the slow balance of oxygen and cold and current, all of it would shift, and the animals could no more see it coming than you could feel the tide turning in your sleep. The rain that felt permanent was, in the long measure of the planet, already moving toward its close. Not yet, not in this scene. Here the water is still warm, and the giants still cruise, and the sunlight still slants down through the drifting shells. Let that image linger, whole and unhurried, before it begins to fade away. So picture the giant not alone, but sharing its water with animals you would recognize as strange cousins. The Cleveland Shale Sea was crowded, and Dunkleosteus was only the most heavily armoured resident in it. To feel its scale, you have to set it beside the neighbours, and the neighbours were remarkable in their own right. Start with the other giant, the one that in older reconstructions could stand shoulder to shoulder with Dunkleosteus. Its name is Titanichthys, a placoderm of the same broad group, the Arthrodires, the jointed neck-armoured fish. For decades, Titanichthys was drawn as a monster, a body once estimated at 23 to 25 feet long. In those older figures it matched Dunkleosteus, or even exceeded it, another tank of bone gliding through the same warm shelf sea south of the Devonian equator. That number has since been questioned, in the same way the size of Dunkleosteus was questioned. The 2023 reanalysis by Russell Engelman, working from head-length proportions in smaller, completely preserved Arthrodires, pulled the estimate down sharply. In that revised view, Titanichthys stood closer to 13.5 feet, roughly 4 meters, a length very similar to the revised figure for Dunkleosteus itself. Both giants shrank on paper at once from the length of a small bus toward the length of a large car. Treat that smaller number as the newer view, not the settled one. The debate is live, and complete bodies of these animals are rare, so the honest position is that both figures still stand side by side in the literature. Whatever its length, Titanichthys was not a second Dunkleosteus in the way that mattered most, which was the mouth, where Dunkleosteus carried those heavy self-sharpening blade plates, edges that wore against each other with every bite. Titanichthys carried something almost opposite. Its lower jaw was narrow. It was toothless in the functional sense, and crucially it lacked cutting edges entirely. A jaw built to shear and crush, and a jaw with no shearing surface at all, belonged to two animals living in the same sea, and that single difference tells you they were not hunting the same way. In 2020, a team led by researchers including Boisvert and Ferron, publishing in Royal Society Open Science, put forward the explanation that fits that strange jaw. They argued that Titanichthys was a suspension feeder, a filter feeder. Instead of biting large prey, it likely swam with its mouth open and strained the water, gathering schools of small fish or clouds of zooplankton from the open column. If that reading holds, and it is a hypothesis rather than a proven fact, then Titanichthys ranks among the earliest large-bodied vertebrate filter feeders known anywhere in the fossil record. Long before the great whales, long before the basking sharks and manta rays that trace slow arcs through modern plankton, an armoured fish in a Devonian sea may have been doing something very close to the same thing. Let that settle for a moment, because it changes how you should hear the word predator. The two biggest armoured fish in this water were not two versions of the same appetite. One was a crusher, a shearer, an animal whose bite force has been modelled in the thousands of newtons. The other, apparently, was a gentle strainer of the smallest living things, moving through the same light, breathing the same warm water, and taking almost nothing that could fight back. Same sea, same size class, opposite mouths. The Devonian was already experimenting with the two great strategies that large ocean animals would use for the next 360 million years. Now shrink your view, because not every neighbour was a giant. Cutting through the middle water, faster and far more familiar in outline, was Cladoselache. This was an early shark, streamlined and lean, and it ran to roughly 6 feet long. Set that against the armoured heads around it, and the contrast is immediate. Where Dunkleosteus was front-loaded, all bone shield and hinged jaw, Cladoselache was smooth from nose to tail, a clean torpedo of muscle with none of the heavy plating that defined the placoderms. If you could hang the two silhouettes side by side in the same shaft of slanting sunlight, one would read as a wall and the other as an arrow. Cladoselache matters for a second reason, one that has nothing to do with size and everything to do with luck. It is known from some of the best preserved early shark body fossils ever found. The black oxygen-poor mud of the Cleveland Shale, the same still and lifeless bottom that preserved Dunkleosteus so completely, did the same favour for this shark. Specimens have come out of that shale carrying impressions of muscle and even of skin. Sharks are built largely of cartilage, which rarely survives, so a fossil that records the shape of the muscle blocks and the texture of the outer body is a rare gift. Much of what is known about how early sharks were actually put together comes from these Ohio slabs. Their preservation is good enough that even the last meals survive. Fossilized stomach contents in Cladoselache show what this 6-foot hunter was eating, and the menu is specific. Small fish, cephalopods, the shelled and soft relatives of squid and nautilus drifting through the same water, and shrimp-like arthropods, the small jointed swimmers of the Devonian column. So here is a third distinct way of making a living in one sea. Not the crushing bite of Dunkleosteus, not the open-mouthed straining of Titanichthys, but the quick pursuit of small active prey by a fast and flexible body. 3 animals, 3 feeding strategies, 1 shared stretch of warm shelf water. Hold all 3 in your mind at once, because together they give the sea its true scale. The armoured heads of the arthrodires provide the mass and the menace. The slim shark provides the speed. And the filter-feeding giant provides the quiet reminder that size in the Devonian did not always mean ferocity. Whichever length estimate you trust for the 2 placoderm giants, whether the old figures near 25 feet or the revised figures near 13.5, the range of body plan stays just as wide. A wall of bone, a strainer of plankton, and an arrow of muscle, all lit by the same sun coming down through the clear upper water before it faded into the black mud below. And this is a good place to pause and say something plainly. Follow or subscribe wherever you're listening, on Spotify, on YouTube, or in your podcast app of choice. It costs you nothing, and it lets these long, slow walks through deep time find the next person who wants to fall asleep inside them. Now return to the water and let the neighbours set the reference frame for the giant. Against Cladoselache at 6 feet, a Dunkleosteus head shield alone, the bony helmet and thorax ran on the order of 2 feet in length, and the animal behind it, even in the smaller revised estimate, would have loomed over the shark like a boulder over a fish. Against Titanichthys, whether the 2 placoderms were both close to 13.5 feet or both stretched toward the mid-20s, you have 2 armoured giants trading the same open water, one built to bite through shell and bone, the other apparently built to take nothing larger than a minnow. The sea was not a single monster and its victims. It was a working community, layered by size and by diet, each animal fitted to a slightly different way of surviving in warm water that stayed in the 70s and 80s degrees Fahrenheit, under a sky with no birds in it and a shore with no grass. There is something restful in that completeness. You're not looking at one creature in an empty ocean. You are looking at an ecosystem that functioned, that balanced predators against prey and giants against the small swarms they fed on. The placoderms held the top of it. Titanichthys strained the bottom of the food web while carrying a body as large as the fiercest hunter in the same water. Cladoselache worked the middle, chasing fish and cephalopods and shrimp-like arthropods through the light. Ammonoids jetted and drifted around them all, some of them the very shelled prey the adult Dunkleosteus could crack open with that fast 4-bar bite. Every layer fed the one above it, and all of it ran on a kind of stability you can almost feel from here. These animals were not brief experiments. The armoured fish had dominated Devonian seas since early in the period, and by this late stretch they had settled into a mature working order, giants and sharks and shelled swimmers turning over in warm, quiet, tropical water year after year, generation after generation, in a world that had found a balance and kept it. The light came down the same way each day. The mud on the bottom stayed black and still and starved of oxygen, killing the scavengers and, as a side effect, saving the dead so completely that we can still read a shark's muscles and a giant's helmet 360 million years later. It is easy, lying here, to imagine that such a world would simply continue, that the crusher, the strainer, and the arrow would keep sharing the same warm sea indefinitely, each fitted to its own quiet task. For a very long time, by any human measure, it did continue. The armoured order held its shape across an immense span of years, steady and warm and full, A whole community of bone and cartilage turning slowly in the shallow light over what would one day be Ohio. Picture the water first before the animal moves at all. Warm, clear, and shallow, somewhere in the 70s or low 80s Fahrenheit. The kind of subtropical sea that once covered the land we now call Ohio. Sunlight comes down through the upper water in long slanting bars, greenish and soft, and the light bends as the surface stirs far overhead. Below that lit ceiling the water grows dimmer by degrees, and in the middle of it, holding almost perfectly still, hangs the armoured shape you have come to know. The Dunkleosteus is not swimming so much as waiting. Its head shield and thorax plates, roughly 2 feet of interlocking bone, catch the slanting light along their ridges. The rest of the body trails behind into shadow, and here you should be honest with yourself about what you can and cannot see. No complete rear body fossil of this animal has ever been found, so the tail behind the armour is a reasoned guess, drawn from smaller relatives, shorter and stouter in the newer reconstructions, perhaps 11 to 13 feet in total for a typical adult. Whatever its exact shape, it moves that hidden body barely at all, a slow flex, a holding of position against the current. You are watching a plausible hour in one animal's day, not a certainty. Keep that in mind as the scene unfolds. Everything here is built from what the bones and the black shale allow us to reconstruct, and no more. The water around it is busy in a quiet way. This is the age of fishes, and the sea is full of them. Jawless fish flicker in loose groups near the lit surface. Ammonoids, shelled relatives of squid and octopus, drift and jet through the middle water, their coiled shells turning slowly as they feed. Somewhere off to one side, a slender shark called Cladoselache, only about 6 feet long, cuts a smooth line and is gone. All of it moves through a strange silence. There are no birds yet, no insects humming over the water, none of the sound-producing land life that fills a modern shore. The only sounds are physical ones, the wash of current, the low percussion of something large feeding in the distance. The Dunkleosteus registers that silence differently than you would. It reads the water as pressure. Every moving body pushes a small wave ahead of itself, and those faint shifts arrive along the animal's flanks and its broad armoured head. So when an ammonoid drifts down out of the brighter water, turning lazily as it comes, the predator does not need to see it clearly. It feels the shape approaching, the slow displacement, the particular rhythm of a shelled animal that has not yet noticed anything is wrong. The ammonoid is a good target for an adult. Juveniles of this species likely took soft-bodied prey and small fish, but a grown Dunkleosteus could handle thick shells, other armoured placoderms, large and difficult food. Its jaws were built for exactly this. Watch how little it does at first. It lets the ammonoid come. The shelled animal drifts closer into the dim column where the big predator waits, and the distance closes to a body length, then less. Nothing about the predator looks tense. That is part of what makes it frightening, if fear is even the right word for something so patient. The armoured head is turned very slightly. The hidden body coils by a fraction, storing a readiness you can sense but not quite see. In the water, pressure builds against the animal's leading edges as the prey approaches, and some threshold, some line the animal has learned or was born knowing, is about to be crossed. Then it happens, and it happens faster than you can properly follow. The mouth does not simply open, it unlocks. The skull of Dunkleosteus worked as a 4-bar linkage, a mechanical arrangement of connected bony levers, and when it fired, the jaws snapped to their widest gape in as little as 20 milliseconds. That is a fraction of a single heartbeat. The whole bite cycle, open and shut, ran somewhere around 50 to 60 milliseconds. By the standards of any fish, living or extinct, that is among the fastest bites ever measured. From your slow vantage, the mouth is simply closed one instant and yawning the next, A dark cavern where a wall of bone had been. There are no teeth inside that mouth. Instead, there are blades. Bony plates in the jaw formed sharp cutting edges, and they were self-sharpening, grinding against one another with every bite so that a fresh edge was always waiting. Now those edges come together on the ammonoid's shell. The force at work here is not gentle. Biomechanical models put the bite in the thousands of newtons, roughly 4,400 at the front of the jaw, and higher still toward the rear plates in large individuals, 5,300, 7,400 and beyond, depending on where the shell sits and how big the animal is. That is a bite comparable to a large alligator, approaching the numbers estimated for a Tyrannosaurus that would not exist for another 130 million years. The shell does not stand a chance. It fails all at once, with a muffled crack that travels only a short way through the water before the silence closes over it again. The blades shear through the coil, through the chambers, through the soft body folded inside. There is a brief cloud, a scatter of fragments and fluid catching the last of the slanting light. The ammonoid, which a moment ago was turning slowly in the current with no notion of what waited below, is simply gone, taken in a single closing of that impossible mouth. Whether suction played a part in drawing it in is genuinely uncertain. Some researchers have suggested that the rapid opening of those jaws created a pull, a sudden expansion that helped draw prey inward the way many modern fish feed. Others doubt that true suction feeding is even mechanically possible for an animal this large and this heavily armoured in open water. So leave that question open, the way the science leaves it. What you can say is that the strike combined speed and shearing force in a way few animals before or since have matched. And now the aftermath, which is the quietest part of all. The predator settles. The jaws close on what they have taken. The head lowers back toward its patient angle, and the hidden body eases out of its coil into that same slow, holding drift. There is no chase, no thrashing, no display. Whatever the animal has swallowed, it processes without ceremony, and it returns almost at once to the business of waiting. The fragments it did not take begin their long fall. Splinters of shell, the lighter pieces of the ruined ammonoid, drift down out of the lit water and into the dimness below. Here the sea changes character. Beneath the bright, moving upper layers, the water grows still and dark and starved of oxygen, and the bottom is not sand or reef, but fine, black mud. That mud would one day harden into the Cleveland Shale, the black marine rock that holds nearly everything we know about this animal. The shell fragments sink toward it slowly, turning as they go, until they reach the boundary where the water stops moving and the blackness begins. Down there, in that anoxic deep, there are almost no scavengers to pick a carcass apart. The lack of oxygen that makes the bottom lifeless is the same chemistry that preserves what falls into it with rare completeness. It is a strange gift, this poisoned floor. It killed the things that would have erased the record, and so it kept the record instead. Somewhere in mud like this, across hundreds of millions of years, the bones and armour of predators like the one you're watching would wait to be read. But the animal above is not thinking about any of that. It hangs in the slanting light, digesting, patrolling, in the loosest sense of the word, its armoured head turned gently into the current. Nearly half of that skull, remember, was not bone at all but cartilage, the jaw joints and muscle anchors made of tissue that almost never fossilizes, inferred only from faint impressions and careful study. So even now, watching it hold so solid and so plated in the green light, you're seeing something partly reconstructed, a creature half recovered from stone and half reasoned back into being. Another ammonoid drifts high in the water, well out of range, coiled shell catching the light as it feeds. A group of small fish scatters and reforms near the surface. The Cladoselache, or one like it, passes again at the edge of vision and slips away. The Dunkleosteus notes the pressure of each of them along its flanks and does nothing. Not everything that moves is worth the effort of that tremendous bite. It can afford to wait. In a sea it dominates. Patience costs it very little. Time passes the way it does for an animal with no reason to hurry. The bars of sunlight shift as the surface stirs. The warm water moves through and around the armoured body, carrying its small messages of pressure and motion. Fragments of the last kill are still settling, somewhere far below, into the black mud that will keep them. And the predator holds its position in the lit column, unhurried, enormous, entirely at home in the quiet, waiting for the next slow shape to drift down into range. This is 1 hour, reconstructed in a life that would have counted such hours by the thousands. Day after day the pattern held, the waiting and the strike and the settling back, across a world of warm shallow seas that stayed much the same for a very long time. For roughly 20 million years this armoured world held together, until the water itself began to turn against everything living in it. For roughly 20 million years this armoured world held together, until the water itself began to turn against everything living in it. For roughly 20 million years this armoured world held together, until the water itself began to turn against everything living in it. The change did not arrive as a single blow. It came in pulses, slow and uneven, spread across a stretch of time between about 372 and 359 million years ago. You would not have felt it in a day, or a season, or a lifetime. You would have felt it the way you feel a tide going out, a little more seafloor bared each time, until one morning the water simply does not come back the way it used to. Settle in now, and let this last chapter move slowly, because the end of a world deserves to be told without hurry. There is no alarm in it, only distance, and the quiet arithmetic of deep time. Let the numbers settle over you like fine black silt drifting down onto the mud. Paleontologists call this long unravelling the Late Devonian mass extinction. The name suggests one catastrophe, but the truth is gentler and stranger. It was a series of crises, separated by long recoveries, each one shaving away a little more of the living world. 2 of these pulses stand out above the rest, and both have names as heavy and cold as the events themselves. The first is the Frasnian-Furmenian crisis, sometimes called the Kellwasser event, which fell near 372 million years ago. The second is the Devonian crisis, the Hangenberg event, which struck close to 358.9 million years ago, right at the boundary where the Devonian gave way to the age that followed. Between the opening of the first and the close of the last, the seas were reordered again and again. Taken together, these pulses are estimated to have removed somewhere between 70 and 80% of all animal species on Earth. Think about that fraction the next time you look at a crowded shoreline. Out of every 10 kinds of creature, 7 or 8 would simply not survive the passage, not overnight. Over a span longer than most of us can hold in the mind, but in the vast clock of the planet, brief. The hardest losses fell in the sea, which is fitting, because the sea was where the Devonian had been most extravagant. Reef systems that had spread for miles, built by corals and by sponge-like animals called stromatoporoids, collapsed and did not rebuild for a very long time. The warm, shallow, clear water reefs that had ringed the tropics thinned out and went quiet. The scaffolding of an entire world was pulled down, one crisis at a time. And here is the part that unsettles even now. We are not certain why. The causes of the late Devonian extinctions remain genuinely, openly debated, and the honest thing is to say so and to sit with the uncertainty rather than paper over it. There is no tidy single villain in this account, no one number to point to. There are instead several suspects, each with real evidence behind it, none of them proven. The first suspect is a lack of oxygen in the water itself. Across large areas of the Devonian seafloor, the deep water appears to have gone anoxic, meaning starved of oxygen, again and again. You can read it in the black shales laid down in those intervals, dark, carbon-rich mud that only forms where almost nothing can breathe. The same chemistry that so beautifully preserved the armoured fish of Ohio may also record the very poison that helped to empty the seas. Picture that suffocation not as a storm, but as a slow ceiling lowering over the deep. Warm water holds less dissolved oxygen than cold water, the way a warm room feels stuffy while a cold one feels sharp and clean. When the deep sea stagnates, the layer of living, breathable water grows thin, and animals adapted to the bottom find themselves pressed upward into a shrinking band. For a giant that hunted across the water column, a thinning of the breathable sea is a quiet kind of cage. The second suspect runs the opposite direction. Rather than heat, some evidence points to cooling, even to episodes of glaciation near the poles. The Devonian had spent most of its length without permanent polar ice, a greenhouse world with warm seas lapping over land that today lies far from any tropic. If ice began to gather at the poles, sea levels would have dropped, and those broad, shallow shelves, the very nurseries of Devonian life, would have drained toward the deeper basins. A predator built for shallow tropical shelves has nowhere good to go when the shelves themselves withdraw. The third suspect is volcanism, the slow bleeding of enormous volumes of lava and gas from within the earth over long intervals. One line of research has even traced spikes of mercury in the rock from around the end Devonian crisis, arguing that volcanic mercury may have poisoned the seas and disrupted the chemistry of life. It is a striking idea, and it is still being tested. Treat it as a hypothesis under examination, not a verdict. And then there is the fourth suspect, the most dramatic and the most speculative, the possibility of a bolide impact, a large body from space striking the Earth. It is raised in the literature, and it cannot be ruled out entirely, but the evidence for it in the Late Devonian is far weaker than for the impact that would end the age of dinosaurs much later. So we mention it calmly and set it in its place. A whisper in the record, not a shout. The likeliest truth is that no single cause did this. Worlds rarely fall for one reason. It may have been anoxia and cooling and volcanism together, each weakening the living sea until the smallest additional stress became the last one it could bear. What matters for our purposes is simply this. The water that had cradled the armoured giants was becoming, pulse by pulse, a place they could no longer rule, because the armoured giants did not survive it. The placoderms, that great tribe of jawed and plated fishes to which Dunkleosteus belonged, had been the dominant vertebrate predators of the Devonian for tens of millions of years. They had appeared early in the period and spread into nearly every marine setting, from open shelf seas to river mouths, and by the time the Devonian closed they were gone, not diminished, gone. An entire major branch of vertebrate life, erased from every ocean on the planet. If you want a single measure of how total the Late Devonian reset was, that is it. Not the death of one famous animal, but the extinction of the whole armoured dynasty it belonged to. The tanks of the ancient sea, every one of them, laid down at last in the mud. Why the placoderms and not others is another open question, and a fascinating one. One idea is that they were, in the end, outcompeted. The same seas held early sharks and early bony fishes, two groups that would go on to inherit the water and hold it right up to the present day. Sharks like the slender 6-foot Cladoselache already swam the Cleveland Shale Sea alongside Dunkleosteus. The bony fishes were quieter then, less imposing, but they carried an evolutionary flexibility that the heavily armoured placoderms may have lacked. There is research suggesting that the extinctions acted like a bottleneck, a narrow gate through which only some lineages passed. On the far side of that gate, the survivors found a world swept nearly clean of competitors, and they radiated outward to fill it. The armoured kings fell, and the fishes that would become nearly every fish you know today swam up through the gap they left. That is the deep irony of the whole affair. The catastrophe that ended one dynasty opened the door for the one that still surrounds us. As for Dunkleosteus terrelli itself, we should be careful and precise, which in paleontology often means admitting the edges of our knowledge. The finest specimens come from the Cleveland Shale, dated to roughly 362.6 to 361.0 million years ago, which places this animal in the late Devonian but not exactly at the final curtain. Whether Dunkleosteus itself was struck down directly by the last Hangenberg pulse, or whether it had already declined and vanished somewhat before that final crisis, is not something the sources let us pin to a single year or even a single event. so we hold the timing loosely. The armoured giant belongs to the twilight of the placoderms, and the exact hour of its own ending is written in a hand we cannot fully read. Let that uncertainty be a comfort rather than a frustration. It means the record is still speaking, still withholding, still worth returning to. If you are drifting now, drift knowing that. And if these long quiet walks through deep time are the kind of thing you want more of, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. Then let your attention loosen again and come back with me to the shore. Because while the sea was struggling through its long crisis, something remarkable was happening on the land beside it, and the two were more connected than they might seem. The Late Devonian was the moment the world grew its first true forests. For most of Earth's history before this, the land had been low and stony and nearly bare, greened only by small primitive plants hugging the wet ground. Then came Archaeopteris, one of the earliest trees with real wood, and it changed the surface of the planet. Its trunks grew more than 3 feet thick, tall pillars of woody tissue standing where nothing so grand had ever stood before. Whole forests of them spread across the coastal lowlands, casting the first deep shade the continents had ever known. Stand beneath such a tree in your imagination and feel how new it all was. No birdsong overhead, because there were no birds, and would not be for well over 100 million years. No hum of insects in the canopy in the way you would know it, no flowers, no grass underfoot, only a low, primitive green horizon of tree ferns and giant horsetails and these first thick-trunked pioneers. The bark would feel rough and strange under your palm, the wood of a design the world was inventing as it grew. These forests did more than cast shade. As they spread and grew and died and were buried, they pulled carbon dioxide out of the air on a scale the planet had never seen. Over roughly 50 million years, the rise of forests is credited with drawing down atmospheric carbon dioxide and lifting the amount of oxygen in the air. And carbon dioxide is a greenhouse gas. Pull enough of it from the sky, and the world begins to cool. So here is the quiet, sweeping connection. The trees reshaping the land may have helped tip the climate that reshaped the sea. The greening of the continents and the cooling of the greenhouse world and the pulses of extinction offshore were not separate stories happening in separate places. They may have been threads of a single fabric, the planet remaking its own chemistry, and the armoured fishes swimming through the consequences without any way to know the cause. Roots taking hold in the mud of a riverbank were, in their slow way, part of the same world-altering process that emptied the reefs miles out to sea. There is something almost tender in that image, if you let it settle. The armoured giant hunting in the warm shallows, and far above the waterline the first forests breathing in the ancient air, each utterly unaware of the other, both bound into the same turning of the world. The predator could crush an ammonite shell in a blink, and it could not sense the trees that were helping to end its kind. And then the Devonian closed, and the placoderms were gone, and the black mud over ancient Ohio settled into stone with their armour sealed inside it. For roughly 360 million years, that stone held its cargo in silence. The sea drained away. The land drifted north across the face of the globe, carrying Ohio slowly out of the tropics toward the place it sits today. Continents gathered and split. Whole other worlds of life rose and fell above that buried layer, the dinosaurs among them, none of them ever guessing what lay pressed in the dark shale beneath. Which brings us, at last, from the ending to the legacy, from the death of a dynasty to the strange afterlife these animals now enjoy in the light. Because Dunkleosteus did not truly disappear. Its armour waited, and in time it was found, and in our own age it has been honoured in ways the animal itself could never have imagined. On December 21st, 2020, the state of Ohio made it official. A bill was signed designating Dunkleosteus terrelli, the official state fossil fish of Ohio, only the second official fossil symbol in the state's history. a creature that ruled a tropical sea more than 360 million years ago, whose bones now rest in the rock beneath modern soil, became an emblem of the very ground it once swam above. There is a rightness to it. The armoured giant of the Cleveland Shale, claimed at last by the place it never left. But the deeper legacy is not a ceremony. It is that Dunkleosteus is still, right now, teaching us things and forcing us to unlearn others. This is not a closed case in a museum drawer. It is living, contested, working science, and the last few years have been some of the most surprising in the animal's long afterlife. For generations, the picture in every book was roughly the same. Dunkleosteus was drawn as a huge shark-shaped monster, its armoured head leading a long, streamlined body, with popular estimates of total length running from about 20 feet all the way to 33 feet. Those numbers came from taking the roughly 2-foot armoured head and thorax, which is nearly all that ever fossilises, and scaling out a shark-like body behind it. It made for a spectacular animal, a wall of bone the length of a school bus. Then, in 2023, a researcher named Russell Engelman at Case Western Reserve University looked hard at that assumption and found it wanting. He pointed out a simple, awkward fact. No one has ever found the complete rear body of a Dunkleosteus. Every long, shark-shaped reconstruction was an inference, a guess bolted onto the one part we actually have. So he tried a different method, using the head-length proportions of smaller, related armoured fishes that are known from complete skeletons. The result was startling. Instead of a 20 to 33 foot torpedo, Engelman's analysis suggested a much shorter, stockier animal, on the order of 11 to 13 feet long for typical adults. Not a lean shark shape at all, but something chunkier, blunter, its great armoured head a larger share of a more compact body. The largest individual known was still estimated as an outlier, reaching perhaps near 28.8 feet, an upper bound rather than a typical size, but the everyday Dunkleosteus, in this view, was closer to the length of a small car than a bus. Now, hold this carefully, because honesty requires it. This revision is not settled consensus. It is a live scientific debate, exactly the kind of argument that keeps a science healthy. Some researchers find Engelman's reasoning persuasive. Others are not convinced and prefer the traditional larger figures or want more evidence before they abandon them. The truth is that until someone finds that missing rear body preserved in stone, the exact size and shape of Dunkleosteus remains genuinely uncertain. So you may picture it long and sleek, or short and stout, and know that the science itself has not finished choosing. The rethinking did not stop with size. In 2025, a follow-up study, again led by Engelman with an international team, reconstructed the full musculoskeletal anatomy of the Dunkleosteus jaw in unprecedented detail. Remember that roughly half of this animal's skull was cartilage rather than bone, the soft framework that normally rots away and leaves no trace. Reading its shape means reading the impressions and channels it left in the bone that survived. What they found was a large bony channel that had carried a major facial jaw muscle, and the arrangement of it looked strikingly like the jaw musculature of modern sharks and rays. It stands as some of the best fossil evidence yet that this ancient armoured fish, separated from living sharks by hundreds of millions of years, may have powered its jaws in a fundamentally shark-like way. An old monster, quietly revealing a familiar design beneath the armour. Like the size debate, this too should be held as fresh and open rather than final. It is a recent finding, part of an ongoing effort to understand an animal we still know mostly from its head. What it tells us most clearly is that the story of Dunkleosteus is not a fixed thing carved in stone. It is being rewritten in our own decade, by people patiently comparing bone channels and body proportions, and it will very likely be rewritten again. That is perhaps the truest legacy of the armoured giant. Not the fearsome bite, not the record-setting jaws, not even the crown of state fossil. It is that a creature dead for more than 360 million years can still surprise us, still overturn what we thought we knew, still change everything we imagined about its own shape. The terrible fish is not finished with us yet. So let the picture in your mind stay soft at the edges. Somewhere in the warm, shallow, vanished sea over ancient Ohio, an armoured shape moves through slanting green light, and we cannot say for certain how long it was, or exactly how it swam, or precisely when its kind slipped away into the black anoxic mud. We know it was there, we know it was extraordinary, and we know the sea it ruled did not fade away all at once, but pulse by patient pulse, over millions of years, in a passing that on the vast clock of the earth counts as barely a geological instant. The armoured dynasty is gone. The reefs it swam past are stone. The warm tropical shelf lies buried and dry and far to the north of where it began. The first great forests that helped tip that lost world have long since turned to coal and dust, and given way to forests of entirely new design. Everything that made that sea a place, the heat of the water, the drift of the ammonites, the silent percussion of a giant feeding in the dark, all of it is beyond any recovering. Consider how much of this animal you have been asked to imagine, and how little of it is truly known. Start with something as simple as its length. For most of a century the number given for Dunkleosteus terrelli was enormous. 20 feet, some said, 30 feet, others, 33 feet at the far edge, longer than a school bus, heavier than a ton. Those figures came from a reasonable guess. Take the armoured head and thorax, roughly 2 feet of interlocking bone, and scale the rest of the body to match a shark. Sharks were the familiar template, so the great fish was stretched into a shark's silhouette, long and tapering, and the imagined tail trailed off into open water. Then, in 2023, Russell Engelman at Case Western Reserve University asked a quiet question. Why a shark? Dunkleosteus was not a shark. It was an arthrodire, a placoderm, and there are smaller arthrodires preserved whole, head to tail, no guessing required. Measure those complete animals. Learn how their head length relates to their total length. Then apply that honest proportion to the giant. When Engelman did this, the great fish shrank, not to 20 feet, to something near 11 to 13 feet for a typical adult, with the very largest known individual pushed to perhaps 29 feet as an outlier, a rare upper bound rather than a normal size. Sit with how large that revision is. A predator you had pictured as 30 feet becomes, in the newer reading, barely more than a third of that. This is not a settled correction. It is a live argument, one method against another, and the older figures still appear in many places. You are allowed to hold both numbers at once. The point is not to know which is right tonight. The point is to feel how much of a vanished animal rests on the choice of a template, and how quietly that choice can be questioned. The same uncertainty runs deeper than length. It reaches the shape of the body itself. Was Dunkleosteus long and lean, a bony head leading a streamlined swimmer, or short and heavy, a thick, blunt animal with the armour making up much of its bulk? The traditional pictures gave it the shark's elongated line. Engelman's revised model argues for something stockier, chunkier behind the head shield, more compact than anyone drew. And here is the fact that keeps the question open. No complete rear body of Dunkleosteus has ever been found. Not one. Everything behind the armoured thorax is inference, borrowed from relatives and from the geometry of the head. The tail you imagine, the depth of the flank, the taper toward the fin, all of it is reconstruction. The armour preserved beautifully because it was bone. The rest was largely cartilage, and cartilage rarely survives 360 million years in the mud. So when you picture this animal gliding through the warm Devonian shallows, be honest with yourself about the edges of the picture. The head is real. The blades are real. The body dissolves into scholarship past the shoulders. There is a second debate, and it concerns not how big the fish was, but how it ate. Everyone agrees on the broad motion. The jaws worked as a 4-bar linkage, 4 connected bony elements that let the mouth snap to full gape in as little as 20 milliseconds. The self-sharpening plates sheared as they closed. That much the fossils and the model support together. The question is whether biting was the whole of it, or only part. Some researchers proposed that the rapid opening did more than expose the blades. When a mouth flies open that fast, it can create a sudden drop in pressure inside, a pull, a suction, that helps draw prey inward before the jaws close. Many modern fish feed exactly this way, snapping open to inhale small prey along with a rush of water. If Dunkleosteus did the same, then the fast gape was a trap as well as a bite, sucking a fish toward the blades in the same instant it revealed them. Others are not convinced this works at such a size. Suction feeding is efficient for small animals in confined bites of water. Scale the mouth up to a predator this large, add the heavy armour and the open sea, and the physics gets harder. The volume you would need to move grows quickly. The seal you would need around the mouth is difficult for so broad and bony a head, so the doubt is reasonable. Perhaps suction assisted the bite for certain prey. Perhaps it contributed little, and the animal simply relied on the raw force of the shear, one of the strongest bites ever modelled for a fish, driving those plates through shell and bone. The honest answer is that the balance between suction and pure bite and shear has not been resolved. You can let the mouth open in your mind either way tonight. Both are guesses wearing the clothes of study. Before we follow this creature into its ending, let me say one quiet thing. If these slow walk through deep time are the kind of thing you want more of, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. Then let the sea close over the thought again, and we will go on. Because the largest debate of all is not about the animal at all. It is about the world that ended, and what did the ending. The Late Devonian did not close with a single blow. It closed in pulses, a series of crises spread across roughly 13 million years between about 372 and 359 million years ago. The two worst have names. The Kelwasser crisis, near 372 million years ago at the Frasnian and Furmenian boundary, and the Hangenberg crisis at the very end near 359 million years ago. Between them, these events erased an estimated 70 to 80% of animal species. A world of fishes thinned to a remnant. And the cause? Here the science opens into several roads at once, none of them fully proven. One road is anoxia, the loss of oxygen from the seas, the water going still and dead in its lower reaches, suffocating the life within it. The black shales that preserve Dunkleosteus so well are themselves signs of that oxygen-poor bottom, which tells you the conditions for both preservation and catastrophe were written into the same mud. A second road is cooling, a drop in global temperature, perhaps a spread of ice, in a world that had run warm and ice-free for most of the period. Some researchers connect this cooling to the rise of the first great forests, the Archaeopteris trees with woody trunks more than a foot thick, drawing carbon dioxide down out of the air across 50 million years, quietly changing the climate offshore even as the fish still thrived. A greening land, cooling the sea it stood beside. A third road is volcanism, vast eruptions loading the atmosphere and the water with their poisons, including studies that point to mercury spread through the oceans as a chemical marker of that violence. And a fourth road, more speculative, quieter in the literature, raises the possibility of an impact, a body from space, though the evidence for this is thin and offered with caution rather than confidence. The truth, as the sources hold it, is that no single trigger has been established. It may have been several of these at once, feeding one another. Cooling driving anoxia, volcanism driving cooling, a world tipped past its balance by more than one hand. This remains an open question, worked on still, and you should not let anyone hand you a single tidy cause and call it settled. The Devonian ended in a way we are still learning to read, which leaves the last uncertainty, and it is the most personal one for this animal. When exactly did Dunkleosteus itself vanish? Placoderms as a whole, the armoured fishes, appeared early in the Devonian and were gone by its close, possibly outcompeted in the end by the sharks and bony fishes that would inherit the seas. But whether this particular giant was struck down directly by the final Hangenberg pulse, or had already faded from the warm shelves before that last crisis arrived, is not something the sources pin down cleanly. The best Ohio fossils sit at roughly 362 to 361 million years old, a little before that final boundary. So it is possible the great predator was already in decline, already thinning from its shallow tropical kingdom, when the last blow fell on a world it had partly left. You are left then, not with an ending but with an approximation of one, a range of dates rather than a moment, a silhouette that dissolves past the shoulders, a number for its length that two careful methods will not agree on, a mouth that may have sucked or may have only sheared, a world that died in stages, from causes still being counted. This is what it means to know an animal only through bone and black shale, across an ocean of time no memory reaches. Every confident sentence you have ever heard about the terrible fish has a quieter sentence standing behind it, holding a question. And that is not a failure of the science. It is the shape of honesty when the witness is stone, and the sea that held the answer drained away before anything lived that could have written it down. What remains now is stone and study, and the slow work of imagining a sea that no living eye will ever see again. What remains now is stone and study, and the slow work of imagining a sea that no living eye will ever see again. So let the water rise around you one last time, not to hunt, not to measure, only to look and then to leave. Begin at the bottom where the black shale lies. This was mud once, fine and soft, settling grain by grain in a deep with almost no oxygen. Nothing stirred it, nothing burrowed through it. That stillness is why the armour kept, and why we know this animal at all. The floor is quiet down here. It was always quiet. Rise a little. Let the black loosen toward grey, then toward a green that is almost light. The armoured giant rests below you now, a shape of interlocking bone, a head shield built like a shut door. No teeth in that jaw, only two blades of bone that sharpen themselves, edge against edge, with every bite it ever took. Let that shape grow small beneath you as you climb. You spent this long hour close to it. You stood inside the 20 milliseconds of its gape, the fastest snap of any fish then swimming. You held the numbers in your hands, thousands of pounds of force gathered at a bony edge, a bite set beside the great crocodiles, and the tyrant lizards that would not arrive for another 130 million years. You do not need to hold those numbers now. Set them down on the seafloor with the animal. They will keep rising. The water warms as you go into the 70s and 80s by feel, a bath with no ice anywhere on the planet to cool it. Sunlight slants down to meet you, broken into moving bars, the way light moves in any warm, shallow sea. Small fish scatter through it, jawless and jawed. Ammonoids drift and jet, coiled shells no larger than your hand. A slender early shark, no longer than a tall man, slips past on business of its own. None of them fear you, you're only passing through, and here, near the middle of the water, let the pace go slack. There is nothing left to prove and nowhere you need to be. If you have been carried along by this quiet company, you can follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice, and the old sea will still be here when you return. For now, just drift. Think of how strange it is that any of this reaches you. An animal that has been gone for some 360 million years, known mostly from its head and its heavy collar of armour, its rear body never found whole, imagined instead from smaller cousins. Even its true length is still argued over, the older picture of a long shark-shaped hunter set against a newer one of something shorter and stouter and thicker through the middle. Scientists are still turning the bones, still finding channels in them where muscle once anchored, still changing their minds in careful, patient ways. The animal is finished, the looking is not. You do not have to settle that argument tonight. Let both shapes hang in the water together, the long one and the stout one, two guesses at a life, both honest, both incomplete. That is how deep time gives itself to you, in pieces, in outlines, in the quiet admission that some of it will never be known. Rise again. The light grows stronger, the water clearer, until the surface waits above you like a bright ceiling. Break through it gently, and let the sea flatten out below into a wide, calm sheet. This is the shallow tropical ocean that once lay over the place now called Ohio, when that ground sat south of the equator under a warm and open sky. Now pull back further, so the water becomes a plain of light, and the low coast slides into view at its edge. There stand the first true forests, the tall trunks of an early tree spreading dark green along the shore. Behind them ferns and giant horsetails, and beyond that, bare stone and silence. No grass anywhere, no flowers, no bird song, because there are no birds, and no insect hum carried out on the wind. The only sounds are water and current, and the low soft weight of a large body moving somewhere out of sight. Hold there a moment above that green and quiet coast. This is the whole world of the armoured fish laid out small beneath you. A warm sea, a low shore, a silence so complete it feels like a held breath. Take one slow breath of your own now, an easy deep breath, and let it out as gently as the tide going back. Higher still. The coast becomes a thin line, the sea becomes a pale gleam. You're far enough now that the animal, the armour, the blades, the fierce and famous bite, all of it folds down into a single point of light on a young planet turning slowly in the dark. Everything you learn tonight lives inside that point. The whole long story of a fish that ruled a vanished sea, no larger from here than a single grain of that black settling mud. In time, that sea will change. The warm shallows will cool and stir, the great armoured kinds will thin and go, in slow pulses across the closing Devonian, until the last of them are gone and the empty water is left to sharks and to bony fish. But you are above all of that now, above the pulses and the losses, high enough that the extinctions read only as a soft dimming, a light lowered by a patient hand. The armoured giants had their long reign. Then gently they let it go, and the sea moved on without them. Let the years move too. Let them run past you in the dark, quiet and countless, until the sea itself dries from the land and the shale hardens into cliffs, and the cliffs stand along a cold northern lake, waiting. All that armour, pressed flat and turned to stone, holding its shape through more time than the mind can truly cross, waiting to be an emblem, a named and honoured fossil of a place that did not yet exist when it lived. You do not need to carry any of it forward. Let the light of that small world go soft. Let the numbers dissolve. Let the fierce jaw ease open one final time and hold still, harmless now, only a shape in old rock under old water in your mind. Let the armoured giant fade away into the deep from which it rose, down through the warm clear upper sea, down past the slanting bars of light, down to the black and silent floor where it has rested all this time, and where it will rest still, long after you have closed your eyes. The sea is calm. The coast is dark and low. The forests stand without a sound. There is nothing here that needs you awake. There is only warm water and slow light, and the long gentle turning of a world that has already kept its secrets safely for hundreds of millions of years, and will keep them a little longer while you rest. Breathe out. Let your body grow heavy, the way the armour grew heavy as it sank. Let the water close soft and warm above you. There is no hunt tonight, no measuring, no reaching, only the drift and the dark and the deep unhurried peace of a sea that asks nothing of you at all. Let it carry you down, slow and easy, into sleep. Sleep well tonight, traveller. Good night.